Czy można prosić Państwa o zajmowanie miejsc? Dzień dobry Państwu. Welcome in the Institute of Physics. It is 70 years of anniversary of the Institute, and strictly scientific part will start at 9:50. However, now is this welcome part, and I think that it will be better if this welcome part will be in Polish, and later on we will switch in English, if it is fine for you. Okay? To ja teraz się przełączę na polski i będę po polsku, a później się przełączymy na angielski, dobrze? Chciałbym bardzo przywitać naszych gości, którzy przybyli na tą uroczystość. Jest z nami pan prezes Polskiej Akademii Nauk, profesor Marek Konarzewski. Polską Akademię Nauk reprezentują dziekan Wydziału III, profesor Janusz Jurczak, profesor Paweł Kulesza, przewodniczący Rady Kuratorów Wydziału III, profesor Izabela Grzegory, zastępca przewodniczącego Rady Wydziału III. Jest z nami profesor Mirosław Karpierz, przewodniczący Komitetu Fizyki Polskiej Akademii Nauk. Chciałbym bardzo serdecznie przywitać panią profesor Ewę Szczepańską-Sadowską, wiceprezesa Polskiej Akademii Umiejętności. Jest mi niezmiernie miło przywitać rektorów zaprzyjaźnionych uczelni, pana profesora Alojzego Nowaka, rektora Uniwersytetu Warszawskiego. Chciałbym przywitać pana profesora Zbigniewa Lalaka, prorektora do spraw badań Uniwersytetu Warszawskiego. Chciałbym również przywitać profesora Arkadiusza Wójsa, rektora Politechniki Warszawskiej. Są z nami przedstawiciele jednostek, które finansują nasze badania i jest nam strasznie miło, że finansują. Chciałbym przywitać pana doktora Jacka Orła, pełniącego obowiązki dyrektora NCBR-u. Chciałbym przywitać panią Kingę Słomińską, zastępcę dyrektora do spraw działalności programowej Fundacji na Rzecz Nauki Polskiej. Jest z nami wiceprezes GUM-u, pan Rafał Kępka. Współpracuje z nami szereg towarzystw naukowych. Chciałbym przywitać panią Teresę Rzącę, prezesa Polskiego Towarzystwa Fizycznego. Chciałbym przywitać panią Agnieszkę Witkowską, wiceprezesa Polskiego Towarzystwa Promieniowania Synchrotronowego. Chciałbym przywitać profesora Piotra Bednarczyka, przewodniczącego Polskiego Towarzystwa Biofizycznego. Chciałbym przywitać profesora Leszka Markowskiego, przewodniczącego Polskiego Towarzystwa Próżniowego. Chciałbym przywitać profesora Piotra Bednarczyka, przewodniczącego Polskiego Towarzystwa Biofizycznego. I profesora Michała Leszczyńskiego, przewodniczącego Polskiego Towarzystwa Wzrostu Kryształów. Urząd Miasta Warszawy reprezentuje pani Karolina Zdrodowska, dyrektor i koordynator do spraw przedsiębiorczości i dialogu społecznego Urzędu Miasta Stołecznego Warszawy. Chciałbym ją serdecznie przywitać. Jest z nami szereg dyrektorów instytutów Polskiej Akademii Nauk, którzy z nami bardzo blisko współpracują. Chciałbym przywitać profesora Tadeusza Burczyńskiego, dyrektora Instytutu Podstawowych Problemów Techniki. Chciałbym przywitać profesora Dariusza Kaczorowskiego, dyrektora Instytutu Niskich Temperatur i Badań Strukturalnych Polskiej Akademii Nauk. Chciałbym przywitać profesora Zbigniewa Trybułę, dyrektora Instytutu Fizyki Molekularnej Polskiej Akademii Nauk. Chciałbym przywitać profesora Michała Boćkowskiego, dyrektora Instytutu Wysokich Ciśnień. Chciałbym przywitać profesora Krzysztofa Pawłowskiego, dyrektora Centrum Fizyki Teoretycznej. Chciałbym przywitać profesora Karola Palkę, dyrektora Instytutu Matematycznego Polskiej Akademii Nauk. Chciałbym przywitać profesora Bogdana Fornala, zastępcę dyrektora do spraw naukowych Instytutu Fizyki Jądrowej Polskiej Akademii Nauk. Witam profesora Adama Kubasa, dyrektora Instytutu Chemii Fizycznej Polskiej Akademii Nauk. Serdecznie witam panią Agnieszkę Wierzbicką, dyrektora Instytutu Genetyki i Biotechnologii Zwierząt Polskiej Akademii Nauk. Witam profesora Rafała Junosze-Szaniewskiego, zastępcę dyrektora do spraw naukowych Instytutu Geofizyki Polskiej Akademii Nauk. Witam doktora inżyniera Piotra Gustka, dyrektora Instytutu Mikroelektroniki i Fotoniki w sieci badawczej Łukasiewicz. Witam pana magistra Mariusza Wielca, dyrektora Cezamatu. Witam profesora Wojciecha Dominika, pełniącego obowiązki dyrektora Centrum Nowych Technologii Uniwersytetu Warszawskiego. Jest z nami szereg dziekanów wydziałów fizyki, nie tylko fizyki, którzy z nami współpracują. Bardzo serdecznie witam profesora Dariusza Wasika, dziekana Wydziału Fizyki Uniwersytetu Warszawskiego. Witam profesora Wojciecha Wróbla, dziekana Wydziału Fizyki Politechniki Warszawskiej. Witam profesor Ewę Gudowską-Nowak, dziekana Wydziału Fizyki, Astronomii i Informatyki Stosowanej Uniwersytetu Jagiellońskiego. Witam profesor doktor inżynier Annę Boczkowską, dziekana Wydziału Inżynierii Materiałowej Politechniki Warszawskiej. Witam profesora Krzysztofa Malarza, prodziekana Wydziału Fizyki i Informatyki Stosowanej Akademii Górniczo-Hutniczej. Witam profesora Józefa Sienkiewicza, dziekana Wydziału Fizyki Technicznej i Matematyki Stosowanej Politechniki Gdańskiej. Jest mi niezmiernie miło przywitać przedstawicieli instytucji, które reprezentują przemysł. Witam pana Andrzeja Wiśniewskiego, prezesa KOMEF-u, spółka z ograniczoną odpowiedzialnością. Witam pana Andreasa Gensla, prezesa zarządu Prewekt, spółka z ograniczoną odpowiedzialnością. Jest mi niezmiernie miło przywitać wszystkich pracowników Instytutu Fizyki Polskiej Akademii Nauk i wszystkich zaproszonych gości i wszystkich pracowników Instytutu Fizyki Polskiej Akademii Nauk. Szczególnie miło jest mi przywitać panią profesor Zofię Białonicką-Birula. Pani profesor jest najstarszym, cały czas czynnym pracownikiem Polskiej Akademii Nauk. Ponieważ pani profesor jest kobietą, to nie będę mówił, ile ma lat. Ale więcej niż historia Instytutu. I to zawodowo czynnej działalności. Chciałbym bardzo serdecznie podziękować Ministerstwu Nauki i Szkolnictwa Wyższego, które jest sponsorem tej imprezy. I to jest możemy się tutaj spotkać dzięki programowi Doskonała Nauka. Ja dostałem list od sekretarza stanu w Ministerstwie Nauki i Szkolnictwa Wyższego, pana Wojciecha Murcka, który pozwolę sobie państwu przeczytać. Szanowny panie dyrektorze, szanowni państwo, szanowni pracownicy Instytutu, szanowni państwo. Proszę przyjąć moje najserdeczniejsze gratulacje oraz życzenia z okazji jubileuszu 70-lecia istnienia Instytutu Fizyki Polskiej Akademii Nauk. Jestem przekonany, że ta doniosła uroczystość stwarza szczególną okazję do wspólnych spotkań, symbolicznych podsumowań, a także określenia planów na przyszłość. Pragnę wyrazić ogromne uznanie dla całokształtu przedsięwzięć realizowanych przez Instytut, a także dokonań, jakie na przestrzeni 7 dekad działalności stały się jego udziałem. Zasłużona jednostka, której tradycje zostały zapoczątkowane przez przedstawicieli wiodących krajowych szkół wyższych, w tym profesora Stefana Pieńkowskiego i profesora Leopolda Infelda, jawi się dziś wspaniałym kontynuatorom tego bogatego naukowego dziedzictwa. Równocześnie pozostaje wiodącym ogólnopolskim centrum prowadzącym badania na najwyższym poziomie we wszystkich dziedzinach współczesnej fizyki. Doceniam dorobek utytułowanej i wysoko wykwalifikowanej kadry skupionej wokół Instytutu, który bezsprzecznie oddziałuje na postęp w zakresie m.in. biofizyki, medycyny, optoelektroniki i technologii cyfrowych, a ponadto pozyskiwania czy gromadzenia energii odnawialnej. Głęboko wierzę, że dzięki wzorowej organizacji, aktywności naukowej, badawczej i wdrożeniowej pracowników oraz wybitnym osiągnięciom w upowszechnianiu wiedzy, Instytut Fizyki to swoista ostoja ponadczasowych wartości akademickich. Szanowni Państwo, ten cenny wkład w rozwój nauki zasługuje na szczególne wyróżnienie. Serdecznie pozdrawiam uczestników uroczystości jubileuszowych. Każdej z osób związanych z Instytutem Polskiej Akademii Nauk życzę satysfakcji z podejmowanych działań, dalszych sukcesów, jak również wszelkiej pomyślności. Podpisano sekretarz stanu Wojciech Murcek. Szanowni Państwo, dostałem szereg, bardzo dużo adresów z różnych instytucji. Ja nie jestem w stanie ich przeczytać, więc ja tylko będę wymieniał. Mam adres z Instytutu Biologii Molekularnej i Komórkowej, podpisany przez panią profesor Marię Miączyńską. Mam adres z Instytutu Medycyny Doświadczalnej i Klinicznej imieniem Mirosława Masakowskiego. To jest podpisany przez panią Leonorę Burzyńską, dyrektora Instytutu. Mam adres z Uniwersytetu Jagiellońskiego, podpisany przez profesora Andrzeja Szytułę. Dostaliśmy adres z Instytutu Sztuki, podpisany przez panią Ewę Dalik-Turek. Adres z Komitetu Fizyki Polskiej Akademii Nauk podpisał profesor Mirosław Karpierz. Adres z Uniwersytetu Śląskiego i z Instytutu Fizyki imieniem Augusta Chełkowskiego podpisał dyrektor Instytutu Sebastian Pawlus. Adres z Polskiego Towarzystwa Promieniowania Synchrotronowego został podpisany przez profesora Wojciecha Kwiatka, prezesa towarzystwa. Adres z Politechniki Warszawskiej został podpisany to jest Wydziału Fizyki Politechniki Warszawskiej, został podpisany przez profesora Wojciecha Wróbla, dziekana wydziału. Adres z Centrum Badań Kosmicznych Polskiej Akademii Nauk został podpisany przez dyrektora Centrum Badań Kosmicznych, profesora Piotra Orleańskiego. Adres z Uniwersytetu Mikołaja Kopernika, adres Uniwersytetu Marii Curie Skłodowskiej został podpisany przez Wiesława. Przepraszam, dostaliśmy adres z Uniwersytetu Marii Curie Skłodowskiej. Adres z Instytutu Chemii Fizycznej PAN został podpisany przez profesora Adama Kubasa, dyrektora Instytutu. Adres z Instytutu Geofizyki Polskiej Akademii Nauk podpisał profesor Paweł Rowiński. Adres z Instytutu Niskich Temperatur i Badań Strukturalnych podpisał profesor Dariusz Kaczorowski. Adres z Instytutu Fizyki Molekularnej Polskiej Akademii Nauk podpisał dyrektor Instytutu profesor Zbigniew Trybuła. Dostaliśmy również adres z Instytutu Fizyki Jądrowej imieniem Henryka Niewodniczańskiego Polskiej Akademii Nauk, podpisany przez dyrektora Instytutu profesora Lesiaka. Po tej takiej części ja myślę, że jest czas, żeby zabrali głos nasi goście i jako pierwszego chciałbym poprosić pana prezesa Polskiej Akademii Nauk, profesora Marka Konarzewskiego. Ja przekażę panu mikrofon. Dobrze.
Panie Dyrektorze, Szanowni Państwo, ja również przygotowałem bardzo piękne, proszę mi wierzyć, pismo, ale oszczędzę Państwu jego treści. Jak się domyślacie, odnoszę się do znakomitej historii Państwa Instytutu, ale w tym miejscu chciałbym zapożyczyć, jeśli Pan Rektor Alojzy Nowak pozwoli, hasło rocznicowe Uniwersytetu Warszawskiego i troszkę je tutaj na potrzeby naszego pięknego spotkania przekuć w słowa. 70 lat, dobry początek. Tak bym chciał, żebyśmy dzisiejsze uroczystości rozumieli. Macie Państwo za sobą 70 lat pięknej historii, ale to, co jest tak naprawdę najważniejsze, to to, co nas czeka w przyszłości. I patrząc w stronę Pana Profesora, nieśmiało powiem, że to, co nas czeka dzięki Państwa wysiłkom, to jest Polska Nagroda Nobla w fizyce. To jest ten cel i to osiągnięcie, które, jak sądzę, powinniśmy mieć przed oczyma i jak sądzę, powinniśmy powiedzieć sobie, że to jest cel w zasięgu naszych rąk i Państwa umysłów. Ja to mówię zainspirowany wczorajszym spotkaniem z prezesem Węgierskiej Akademii Nauk, którego gościłem. Mieliśmy spotkanie Grupy Wyszehradzkiej Akademii i oczywiście gratulowałem panu prezesowi 2 nagród Nobla z węgierskimi nazwiskami. Jednym z tych laureatów, jak Państwo wiecie, jest fizyk węgierski. Drugim laureatką jest Kathleen Kariko, biolożka, dzięki której mieliśmy szczepionkę mRNA przeciwko COVID. Jako prezes Akademii bardzo bym sobie życzył, żeby kiedyś ktoś mi mógł jeszcze za mojej kadencji najlepiej składać również gratulacje i żeby to były gratulacje odnoszące się do polskiego noblisty. I jak sądzę, patrząc naturalistycznie, to właśnie fizyka jest tą dziedziną, w której możemy na to liczyć. Polskie nazwiska, przepraszam, że w stronę pana profesora Dietla się tu skłonię, w tych rozważaniach się pojawiają, więc myślę, że jeśli tylko pomożemy tym najbardziej wybitnym wśród Państwa, to będziemy się cieszyć tym ogromnym osiągnięciem i jestem pewien, że w tym osiągnięciu ogromny, a jeśli nie absolutnie kluczowy wkład będą miały prace, które wywodzić się będą z Państwa Instytutu, bo jesteście placówką absolutnie najlepszą i predestynowaną do tego, żeby właśnie z Państwa grona można było myśleć o kimś, kto kiedyś nas tak bardzo ucieszy. Ale przy okazji pozwólcie sobie Państwo, że na dosłownie 2 minuty refleksji odwołam się do przykładu pani Kariko, bo jest mi bliższy, bardziej go rozumiem. Wspominał mi również pan prezes Front o swojej niedawnej rozmowie, mówi mi o swojej niedawnej rozmowie z nowo powołanym ministrem nauki węgierskim i tenże pan minister powiedział w trakcie tego spotkania, że on widziałby naukę uprawianą w taki oto sposób, że stawiamy sobie konkretny cel i następnie ten cel realizujemy za pomocą potencjału, jaki mamy, instytutów i tak dalej. I że to jest najważniejsze, żeby ten cel był tak sprecyzowany, żebyśmy mogli wokół niego skupić szybko wysiłki, potencjał i to się wtedy uda. I w odpowiedzi na no, wydawałoby się dosyć jasno sformułowaną tezę pan prezes Akademii powiedział, no dobrze, tylko wyobraźmy sobie taką sytuację, jaką właśnie w ostatnich latach jakiej musieliśmy sprostać przy COVID-zie i przy poszukiwaniu szczepionki. Pani doktor Kariko zaczęła swoje prace nad mRNA w latach 80. w zupełnie niszowym wtedy, niepostrzeganym jako czołowym fragmencie biologii molekularnej i jak Państwo być może wiecie, uprawiała to z ogromną determinacją wbrew wszystkim przeszkodom, bo przecież nie miała grantów, bo przecież bardzo trudno publikowała swoje wyniki i gdyby przyjąć tą perspektywę pana ministra, no to okazałoby się, że cel mamy, tak? Natychmiast nam jest potrzebna szczepionka, tylko że nie mamy wiedzy, jak tą szczepionkę uzyskać i dopiero cofając się wstecz do takich właśnie bardzo fundamentalnych prac, które w momencie, kiedy powstawały, trudno było umieścić w jakimś kontekście konkretnego celu, to dzięki temu właśnie, że te prace były prowadzone, można je było potem bardzo szybko wdrożyć i bardzo szybko znaleźć odpowiedź i ten cel zaadresować, jakim było utworzenie szczepionki. I mówię o tym dlatego, że jest to doskonały przykład niedoceniania, czy bardzo takiej spaczonej perspektywy uprawiania nauk podstawowych, którymi się przecież Państwo zajmujecie, którymi ja się też zajmuję, gdzie no, patrzenie w przyszłość i formułowanie celów bez uwzględnienia tego, że ten substrat, dzięki któremu cele są realizowane, musi być gdzieś znacznie wcześniej. Jestem pewien, że ta Nagroda Nobla, o której tutaj mówię, również wyrośnie z dokonań Państwa już tych mieszczących się w 70 latach Państwa aktywności. To nas wszystko i mnie bardzo umocniło w takim prostym przeświadczeniu, że w dyskusjach, które pewnie są też bardzo szybko przed nami z nowo powołanym ministrem bądź panią minister nauki, ja też, jeśli będę miał okazję, a myślę, że będę już niedługo takie rozmowy prowadził, to wskażę dokładnie to samo, że finansowanie nauk podstawowych, tych, którymi się Państwo zajmujecie, którymi się wszyscy zajmujemy, jest solą ziemi naukowej. Bez niego nie będzie ani tych nagród Nobla, ani również odpowiedzi na bardzo palące pytania, takie jakie powstały w czasie pandemii COVID-19, kiedy trzeba było w ciągu dosłownie paru miesięcy stworzyć technologie, dzięki którym szczepionka powstała w zawrotnym, naprawdę w zawrotnym tempie. Także życzę Państwu bardzo właśnie tego 70-letniego początku z takim, no nie powiem, że końcem, ale jednak częściowym uwieńczeniem Państwa wysiłków i tego, że spotkamy się tutaj w tym miejscu za, mam nadzieję, niedługie lata, świętując już nie tylko kolejną okrągłą rocznicę istnienia Państwa Instytutu, ale właśnie Polskiego Nobla w fizyce. Bardzo dziękuję.
Dziękuję bardzo, panie prezesie. Ja bym chciał teraz poprosić pana profesora Alojzego Nowaka, rektora Uniwersytetu Warszawskiego, o zabranie głosu.
Dziękuję bardzo, panie profesorze. Dzień dobry państwu, panie dyrektorze, panie prezesie, panie i panowie profesorowie, szanowni państwo. To dla mnie wielki honor i zaszczyt móc dzisiaj stanąć przed państwem, żeby powiedzieć państwu dziękuję. Dziękuję państwu w imieniu swoim, w imieniu Senatu Uniwersytetu Warszawskiego, w imieniu całego środowiska, ale sądzę, że także szerzej. Za wszystko to, co państwo robicie. Za to, że państwo objaśniacie świat, za to, że państwo ulepszacie świat, za to, że możemy zrozumieć, jak ten świat funkcjonuje. I dzięki wam, dzięki Instytutowi, dzięki fizykom, bo to jest pokłon nie tylko dla Instytutu, ale dla fizyków polskich i w ogóle szerzej dla fizyków na świecie. Dzięki wam żyje nam się lepiej, żyje nam się ciekawiej. Fizyka jest dyscypliną chyba jedną z najpiękniejszych, jeśli nie najpiękniejszą. Fizyków, absolwentów fizyki spotyka się właściwie wszędzie. Ja często o tym wspominam, ponieważ sam jestem ekonomistą i finansistą z wykształcenia, że kiedy byłem na Uniwersytecie w Chicago, to najwięcej wokół mnie było fizyków. Fizyków, którzy objaśniali zjawiska finansowe, którzy wraz z matematykami pisali wzory i pisali formuły zabezpieczające przed ryzykiem. Fizycy, którzy objaśniali związki, które zachodzą pomiędzy gospodarką realną i gospodarką nierealną, jeśli tak można powiedzieć. To jest ogromny wkład państwa, wszystkich i każdego z osobna w to, że także gospodarka w różnych miejscach na świecie funkcjonuje lepiej. Ja dzisiaj jestem zafascynowany państwem, instytutem, który jest w Polskiej Akademii Nauk, ale który jest tak bardzo bliski Uniwersytetowi Warszawskiemu. Bo jak mi Darek Wasik powiedział, dziekan, wszyscy niejako wyrośliśmy z chorzej. Fizycy dali tak wiele także w formie organizacyjnej Uniwersytetowi Warszawskiemu, ale myślę szerzej w Polsce i na zewnątrz. Dali wielu rektorów, wielu znakomitych senatorów. Dali osoby, które sformułowały funkcjonowanie Uniwersytetu Warszawskiego. Państwo, ale także nasi fizycy. I jak dzisiaj słyszę, fizycy także z innych ośrodków, pokazujecie też rzecz ważną, jak współpracować ze sobą, jak tworzyć związki, jak objaśniać świat, jak dyskutować, jak różnić się, jak pięknie różnić się. To, co u was mnie fascynuje, także w Instytucie Fizyki Polskiej Akademii Nauk i u naszych fizyków. Wy też jesteście naszymi fizykami. Ja mam poczucie, że jesteście częścią, piękną częścią, swobodną tego grona fizyków, także Uniwersytetu Warszawskiego. Chciałbym, żebyście mnie dobrze oczywiście rozumieli. To nie chodzi o przynależność, podległość instytucjonalną, ale chodzi o myśl, chodzi o koncepcję postrzegania świata, chodzi o pewne wizje, które się prezentuje. Nigdy właściwie nie słyszałem o przeogromnych kłótniach, o zawiściach wśród fizyków, tak jak czasami się słyszy w innych dyscyplinach. Fizyka dla nas jest teraz fascynująca także z innego powodu. Jak Państwo wiecie, na Uniwersytet wrócił Wydział Lekarski po wielu latach. On był jednym z pierwszych, był częścią, ale w latach 50. postanowiono budować system edukacji na wzór radziecki i wyprowadzono medycynę z Uniwersytetu Warszawskiego. Medycyna bez fizyki nie może się rozwijać. To widać gołym okiem. Bez fizyki różnej, w różnych odmianach, którą Państwo uprawiacie, niemożliwy jest rozwój medycyny. To wy pokazujecie analizy, to wy pokazujecie związki. Oczywiście we współpracy także z kolegami z biologii, z chemii i matematyki, sztucznej inteligencji, informatyki. To jest przecież oczywiste. Ale fizyka nadaje ton, w moim skromnym odczuciu, to co widzę już po krótkim okresie funkcjonowania Wydziału Lekarskiego na Uniwersytecie Warszawskim. To właśnie także dzięki wam człowiek może czuć się bezpieczniej. Człowiek może żyć lepiej. A to jest przecież najważniejsze. Poza ogromnymi odkryciami, których dokonujemy, to jest zresztą fascynujące, że jeśli jest ktoś wierzący, to jednym skinięciem opatrzność stworzyła taki świat, który tak pięknie można teraz odkrywać. Jeśli ktoś jest niewierzący, to przyroda stworzyła ten świat, który my teraz odkrywamy i dochodzimy do tego, żeby go jak najlepiej wykorzystać dla potrzeb człowieka. Absolutnie się zgadzam z tym wszystkim, o czym było także mówione, że finansowanie fizyki w szczególności, ale nauki jest konieczne, musi być zwiększone, bo bez nauki, bez uprawiania nauki, bez kultury prowadzenia badań świat był, jest i może być ograniczony. My tego nie chcemy. Zabiegamy podobnie jak wasz dyrektor, jak wasz pan dyrektor, jak prezes panu, także i na uniwersytecie i w innych miejscach, żeby to wszyscy zrozumieli. Czy tak się stanie? Nie wiem, ale trzeba o to zabiegać i trzeba o to dbać. A zatem życzę Państwu dobrych czasów, dalszego rozwoju. Nie wiem, czy kolejnych 70, czy 200, czy 250 lat. Życzę także i wierzę bardzo głęboko w to, że Nagroda Nobla się pojawi. Ale też wiem rzecz jedną, że my musimy wszyscy działać na rzecz Nagrody Nobla. To nie wystarczy mieć osiągnięcia. Ja rozmawiałem z moimi kolegami z ekonomii, którzy po to, żeby otrzymać Nagrodę Nobla, podchodzili albo wskazywali osoby 7- albo 10-krotnie. Działali na tę rzecz wszyscy. Instytut, uniwersytet, ministerstwo, kraj, państwo, ale także zagranica. To trzeba tworzyć lobby, które prezentuje wyniki, prezentuje osoby i prezentuje miejsce, w którym Nagrody Nobla powstają. I mogę powiedzieć na pewno w imieniu Uniwersytetu Warszawskiego, że będziemy czynić wszystko, żeby tak było. Że będziemy wspierać waszych kandydatów, że będziemy liczyć, żebyście państwo wspierali naszych wspólnych kandydatów, żeby stworzyć potężne, poza wiedzą, poza wysokim poziomem badań i nauki, stworzyć także coś, co może nieładnie się nazywa, ale lobby takie, które będzie wspierało najlepsze osiągnięcia i najlepszych ludzi. Bardzo jestem szczęśliwy, że mogę państwu pogratulować 70-lecia tych ogromnych sukcesów. Bardzo państwu chcę podziękować za bardzo bliską współpracę z Uniwersytetem Warszawskim. Bardzo życzę nam, Uniwersytetowi i państwu, i Instytutowi i w ogóle Polskiej Akademii Nauk dalszej dobrej współpracy. I z tej okazji w imieniu Senatu Uniwersytetu Warszawskiego z wielką przyjemnością chciałem wręczyć okazjonalny medal Uniwersytetu Warszawskiego dla Instytutu Fizyki Polskiej Akademii Nauk. Tutaj, panie dyrektorze, jest wszystko napisane, plus adres, który też pozwoliłem sobie napisać. Gratuluję sukcesów, życzę dalszych sukcesów i życzę wszystkiego najlepszego dla pana dyrektora, dla dyrekcji i całego Instytutu. Dziękuję bardzo. Dziękuję państwu.
Chciałbym teraz poprosić panią Karolinę Zdrodowską z Urzędu Miasta Stołecznego Warszawy o zabranie głosu.
Szanowni Państwo, Panie Dyrektorze, Panie Prezesie, Panie Rektorze, Panie i Panowie Profesorowie, wszyscy pracownicy Państwowej Akademii Nauk, a szczególnie Wydziału Fizyki, wszyscy szanowni goście. Moje przemówienie będzie troszkę bardziej formalne, ponieważ ja mam zaszczyt odczytać list pana prezydenta Rafała Trzaskowskiego, prezydenta Miasta Stołecznego Warszawy, kierowany do Państwa za pośrednictwem pana dyrektora właśnie z okazji tego wspaniałego jubileuszu. Szanowny Panie Dyrektorze, z okazji jubileuszu 70-lecia Instytutu Fizyki Polskiej Akademii Nauk mam zaszczyt złożyć wszystkim pracownikom, naukowcom i współpracownikom serdeczne gratulacje oraz najlepsze życzenia. To niezwykłe osiągnięcie świadczące o wieloletniej pasji i determinacji. Jest to okazja do docenienia roli badaczy i badaczek, którzy pracują w Instytucie oraz wyrażenia wdzięczności za ich zaangażowanie i trud w dążeniu do rozwoju fizyki w Polsce. Od momentu powstania w 1953 roku Instytut stał się pionierem w dziedzinie fizyki nie tylko w kraju, ale także na arenie międzynarodowej. Państwa osiągnięcia w dziedzinie badań, a także w dziedzinie edukacji są inspirujące, godne uznania i mają istotny wpływ na rozwój nauki oraz technologii w Polsce. Instytut prowadzi badania między innymi nad materiałami nowej generacji, a także nanotechnologią, które są niezwykle cenne w dzisiejszym świecie. Osiągnięcia w tym obszarze przyczyniły się do rozwoju nowych materiałów o unikalnych właściwościach, które znajdują zastosowanie w technologii i przemyśle. Przy tej wyjątkowej okazji życzę Instytutowi Fizyki P.A.S. kontynuacji owocnych badań, które przyniosą nowe odkrycia i innowacje oraz będą powodem do dumy. Rewolucja cyfrowa, w tym rozwój technologii opartych na sztucznej inteligencji, stawia przed nami wyzwania dotyczące metod kształcenia i prowadzenia badań naukowych. Jestem przekonany, że społeczność Instytutu Fizyki P.A.S. będzie dumą na naukowej mapie Warszawy, a badacze i badaczki będą potrafili wykorzystać szanse, które daje nam postęp technologiczny. Niech ta rocznica będzie momentem podsumowań oraz punktem wyjścia do kolejnych pełnych sukcesów lat działalności naukowej. Jeszcze raz serdecznie gratuluję Instytutowi Fizyki Polskiej Akademii Nauk 70 lat wpływu na polską naukę. Życzę Państwu inspiracji, determinacji i kreatywności w realizowaniu innowacyjnych badań naukowych i zadań Instytutu. Z wyrazami szacunku, Rafał Trzaskowski.
Dziękuję bardzo. Jest mi strasznie niezmiernie miło. Ja teraz chciałbym poprosić pana profesora Tadeusza Burczyńskiego, który jest przewodniczącym Rady Dyrektorów Instytutów Panowskich, pracownik Instytutów, tak, pan Polskiej Akademii Nauk i reprezentuje coś, z czym najbardziej współpracujemy, instytuty. Proszę bardzo.
Dziękuję bardzo. Dokładnie to jest Rada Dyrektorów Jednostek Naukowych Polskiej Akademii Nauk, czyli trochę szerzej niż samych instytutów. Jakbym chciał właśnie w imieniu tej Rady, której zresztą członkiem jest pan profesor Puźniak, złożyć serdeczne gratulacje z okazji tak pięknego jubileuszu. Naszym zdaniem Instytut Fizyki Polskiej Akademii Nauk należy do jednych z najbardziej aktywnych i wyróżniających się wysokim poziomem naukowym Instytutów Polskiej Akademii Nauk. Proszę Państwa, może nie wszystkich osób, które nie pracują w Akademii, sama struktura instytutów jest troszkę niejasna. W sumie jest 69 Instytutów Polskiej Akademii Nauk. Każdy z nich ma osobowość prawną i dużą autonomię i samodzielność, a jednocześnie są instytutami właśnie Akademii Nauk, bo dyrekcja instytutu jest wyłaniana w wyniku konkursu i każdy dyrektor ma nominację pochodzącą od prezesa. Trzy tygodnie temu odbył się zjazd wszystkich dyrektorów Instytutów Polskiej Akademii Nauk w Wierzbie na Mazurach. To jest ośrodek pracy twórczej Polskiej Akademii Nauk. W trakcie tego spotkania, które w takiej formule, jak się odbyło, było chyba po raz pierwszy, dyrektorzy instytutów podjęli dwa stanowiska. Jedno dotyczyło, to był koniec września, 29-30 września, podjęliśmy takie stanowisko, które dotyczyło wyborów do Sejmu i Senatu. Mogę z satysfakcją powiedzieć, że to nasze stanowisko było skuteczne, bo to, co się stało 15 października, potwierdziło nasze oczekiwania. Ale podjęliśmy także drugie stanowisko, które podejmujemy trochę z bólem serca, dlatego że ono dotyczy spraw finansowych instytutów Polskiej Akademii Nauk, które są w bardzo trudnej sytuacji finansowej. Ja mam to stanowisko przy sobie tutaj i ono zostało podpisane, zostało przygotowane przez Radę Dyrektorów, ale przyjęte przez wszystkich dyrektorów obecnych na tym zjeździe i w nim postulujemy zapewnienie stabilnego funkcjonowania jednostek naukowych PAN poprzez zwiększenie subwencji, zapewnienie równoprawnego dostępu do wszelkich strumieni finansowania przeznaczonych na rozwój nauki, w tym programów typu Inicjatywa Doskonałości oraz zapewnienie dodatkowych środków finansowych na realizację planów rozwojowych. To kierujemy jak tu mam napisane, do prezesa Rady Ministrów, do ministra edukacji i nauki, do ministra finansów, do posłów i posłanek i senatorów. Właściwie chyba to zostało stanowisko upublicznione między innymi przez forum akademickie, natomiast myślę, że będzie to dobry także materiał dla naszej Rady, dla władz Akademii, dla nowych władz państwa i dla nowych władz ministerstwa, które będzie kierowało nauką. Ta sprawa jest o tyle ważna, że niektóre instytuty Polskiej Akademii Nauk znajdują się w bardzo krytycznej sytuacji. Aby trwać dalej i móc rozwijać te obszary nauki, z którymi są związane. Ja mam nadzieję, że właśnie te zmiany polityczne, a także ta nasza aktywność przełoży się na zmianę pozycji instytutów naukowych w sensie finansowania, dlatego że w tym stanowisku, o którym tutaj mówię, zwracamy uwagę, że Polska Akademia Nauk poprzez swoje instytuty jest uważana za najlepszą instytucję naukową w Polsce, co pokazują rankingi międzynarodowe. Na przykład Nature Index pokazuje wyraźnie, że instytuty panowskie razem wzięte są taką instytucją naukową, która jest najwyżej oceniana ze wszystkich instytucji naukowych w Polsce. To ma swój wymiar. To wynika także z tej struktury, która jest nietypowa, ale która daje dużą swobodę i do kreacji nowych teorii. No i także do tego, o czym tu mówił pan prezes Polskiej Akademii Nauk, do tego, abyśmy doczekali pierwszego noblisty właśnie z fizyki. Gratulując raz jeszcze tego pięknego jubileuszu, chciałbym tylko wrócić o 70 lat wstecz. To był okres dosyć chyba ponury w Polsce, 1953 rok. Wtedy powstało wiele instytutów Polskiej Akademii Nauk. To było mniej więcej kilka miesięcy lub rok po powstaniu Polskiej Akademii Nauk. Ale widać, że te instytuty istnieją, rozwijają się i są w doskonałej formie, jeśli chodzi o uprawianą naukę. Ja co najmniej znam kilka instytutów, które właśnie w tym roku taki jubileusz obchodzą, łącznie z instytutem, który sam prezentuję, Instytutem Podstawowych Problemów Techniki. Składając ten adres i życzenia dla Instytutu Fizyki, chciałem tylko przy okazji złożyć też adres w imieniu Instytutu Podstawowych Problemów Techniki. Myśmy obchodzili 3 tygodnie temu taki sam jubileusz. Natomiast w kontekście relacji fizyki i nauk technicznych chciałem powiedzieć, że w naszym Instytucie Podstawowych Problemów Techniki zatrudnionych jest bardzo wielu fizyków. Ja sobie nie wyobrażam, jak można rozwijać nauki techniczne bez fizyki. Więc ta współpraca, którą tu mamy razem z panem dyrektorem, owocuje, będzie owocować i w imieniu Instytutu Podstawowych Problemów Techniki, jego dyrekcji oraz pracowników chciałbym pogratulować tego pięknego jubileuszu i życzyć, aby ta współpraca z nami rozwijała się jak najlepiej. Dziękuję bardzo.
Szanowni Państwo, na tym samym terenie, na którym my jesteśmy, działa Centrum Fizyki Teoretycznej i nasza symbioza trwa 40 lat. Chciałbym prosić pana profesora Iwobirula Białyńskiego, który był pierwszym dyrektorem Centrum Fizyki Teoretycznej, o zabranie głosu.
Ja chyba nie muszę nawet na trybunie stawać. Wymusiłem na panu dyrektorze to, żebym mógł parę słów powiedzieć, ponieważ uważam, że Centrum Fizyki Teoretycznej, które powstało tutaj na tym terenie, bardzo dużo zawdzięcza Instytutowi, aczkolwiek na samym początku potrzeba było innych działań, bo myśmy zostali utworzeni w przeddzień stanu wojennego, kiedy wszystko się sypało naokoło i nie było żadnych szans, żeby centrum, które na papierze powstało, nazywało się wtedy Zakładem Fizyki Teoretycznej, mogło zaistnieć, bo nie miało adresu. I tutaj z pomocą przyszedł nam sekretarz 3. Wydziału. Wtedy Akademią rządzili sekretarze, nie prezes, nie dziekani, tylko sekretarze. Sekretarzem Wydziału 3. był Jan Rychlewski. Bardzo ciekawa postać, mógłbym o tym sporo powiedzieć. I Jan Rychlewski uznał, że jego celem będzie utworzenie tego zakładu, tego centrum. Wszystkie instytuty Akademii odmówiły nam udzielenia jakichś lokali. No i wtedy Jan Rychlewski, który w tenisa grywał z wicepremierem Kopciem, uzyskał zgodę wicepremiera, który to wicepremier Kopeć polecił Instytutowi Technologii Elektronowej, który się mieścił wtedy częściowo na 3. piętrze, żeby przekazał 2 pokoje i mieliśmy w ten sposób adres. Później nasza z Instytutem więź rozwijała się już w cieniu stanu wojennego. 2 pokoje oczywiście to było wystarczające dla dyrekcji, ale mieliśmy już wtedy kilku pracowników i potrzebny nam był większy lokal. I wtedy Jurek Kołodziejczak, ówczesny dyrektor Instytutu Fizyki, polecił panu dyrektorowi technicznemu Jerzemu Jerszynie, o nim to można spokojnie też sporo ciekawych rzeczy powiedzieć. Tak, to był normalny szpieg, który działał na terenie Berlina, ale nie, ekonomiczny, nie taki, co biega z pistoletem, ale ekonomiczny. I potem popadł w niełaskę, mnie się żalił, że to Jaruzelski go utrącił. Otóż pan dyrektor Jerszyna nakazał brygadzie remontowej, Instytut wtedy miał brygadę remontową, wszystkie instytuty miały tego typu instytucje, która to brygada remontowa w ramach działalności gospodarczej, która była takim wytrychem, bo jak działalność gospodarcza, to nie trzeba żadnych pozwoleń i bez żadnych pozwoleń, bez żadnych dokumentacji powstał baraczek dla nas, w którym świętowaliśmy wszyscy wybuch stanu wojennego. Później korzystaliśmy na wszelkie możliwe sposoby z Instytutu Fizyki. Bo jak nasza jednostka nie miała takich różnych możliwości. Zacznę może od stołówki, potem była pani doktor. Potem był faks. Komunikacja z krajami Zachodu odbywała się przy pomocy faksu. No i oczywiście była nieoceniona pani Małgosia, która wypłacała nam pensję, bo myśmy nie mogli jeździć do banku, bo nie mieliśmy odpowiedniego pracownika, który jeszcze musiał mieć jakąś ochronę. Także korzystaliśmy w pełni z tych wszystkich bonusów, które nam Instytut dał i ja chciałem naszą wdzięczność, naszego centrum Instytutowi za to przekazać. Panie dyrektorze, mam nadzieję, że nadal będziemy tutaj.
Ja myślę, że będzie jeszcze lepiej.
Tak, będzie jeszcze lepiej. Proszę bardzo, wręczam panu.
Dziękuję bardzo. Mamy jeszcze jedno wystąpienie, które będzie wygłoszone przez pana profesora Güntera Bauera i ono będzie w imieniu Austriackiej Akademii Nauk, więc ja od tej pory przejdę na angielski. Tym bardziej, że później już będzie część naukowa i wszystkie wykłady są po angielsku, łącznie z wykładami z historii Instytutu. Będzie to angielska historia Instytutu. Może inna od polskiej, ale dobrze. I would like to invite Professor Günther Bauer, who will give an address from the Austrian Academy of Sciences.
Dear Professor Puźniak, distinguished colleagues, directors, presidents, I'm sorry I didn't get all these Polish titles. It's a real pleasure for me to be here again at this institute, which I have visited in the past very often and have very pleasant memories. And today I'm here on behalf of the Austrian Academy of Sciences, in particular of the president and the vice president, Ulrike Diebold, who is a surface physicist, to convey congratulations to these many years of excellent scientific work which has been performed at this Institute of Physics of the Polish Academy of Sciences. In addition, I would like to mention that actually several Austrian groups, in particular working in semiconductor physics, have enjoyed a very fruitful cooperation with physicists from this institute. They started already in these early 1970s with work on narrow gap semiconductors and continued with semi-magnetic and diluted magnetic semiconductors, finally magnetics semiconductors, and recently also on topological insulators. The Austrian groups at several universities in Vienna, Leoben, Innsbruck, and Linz were very pleased to cooperate with this institute and got a lot of specimens, but also benefited a lot from this excellent experimental and theoretical work which was carried out at this institute. And on behalf of this Austrian semiconductor physics community, I would like to extend my gratitude and best wishes for a prosperous scientific future of this institute, not only for the next 70 years, but far beyond as well. Now, it will be difficult for me. Dziękuję Państwu za uwagę, a jeszcze bardziej za te lata współpracy z wieloma polskimi fizykami. Niech Wam gwiazdka pomyślności nigdy nie zagaśnie.
Thank you very much. Thank you. It was excellent. So I think that now is time to start a scientific part, and in the scientific part the first lecture will be given. O, przepraszam bardzo.
Przepraszam, bo Unipres nie napisał adresu, ale Unipres ma dla Instytutu Fizyki statuetkę. Ja może przeczytam, co jest napisane. Pięknych i ważnych, nie wziąłem okularów oczywiście, tak, pięknych i ważnych
naukowych odkryć oraz wszelkiej pomyślności z okazji 70-lecia Instytutu Fizyki P.A.S. życzą dumni ze wspólnych korzeni przyjaciele z Unipresu. 20 października 2023 rok. Rzeczywiście te wspólne korzenie to jest prawda, bo Unipres w pewnym sensie wykiełkował z Instytutu.
Tak, Unipres powstał dzięki Instytutowi w 1972 roku. Profesor Kołodziejczak podpisał decyzję o powstaniu Instytutu i potem przez ponad 30 lat wszystkie doktoraty i habilitacje były przed Państwa Radą Naukową bronione. Także w imieniu wszystkich pracowników Instytutu chciałem się Państwu bardzo nisko ukłonić.
Dziękuję bardzo. Ja przepraszam, że powinienem zauważyć. Dobrze. So we will switch to scientific part. The first lecture will be given by Professor Tomasz Dietl, and it will be about 70 years of the history. Nevertheless, I would like to switch chairman of the conference. So from this time, chairman of the conference will be Piotr Dewar, Vice Director for Scientific Efforts of the Institute of Physics.
Okay, thank you, Roman. We have feedback. Sure why. Okay, so since we're switching to English, thank you for everybody who doesn't speak Polish and lasted through the initial part. I can see a lot of distinguished guests and friends of the Institute here. So I'd like to just say from the Institute that thank you very much for coming to our celebration of these 70 years. It's a great pleasure to have you here. And I'd like to introduce our first speaker in this more scientific session, Professor Tomasz Dietl. He has many outstanding contributions to solid-state physics, low-temperature physics, and especially the development of spintronics. He got his PhD in 1977 at the Institute of Physics. He's a full member of the Polish Academy of Sciences, and he's actually one of the most cited scientists in Poland, and certainly at our institute. He's the winner of many prizes, including the Europhysics Prize in 2005, and notably the Prize of the Foundation of Polish Science in 2006. So this is Poland's top science award. We have a couple of other laureates of this prize here with us today as well, who you'll meet in future talks. He's been the head of the MagTop Center since 2017. This is a major division of the Institute, which is funded by the International Research Agendas Program of the Foundation for Polish Science. It was the first such center founded, in fact. And so, Professor Tomasz Dietl, over to you.
Thank you very much. Thank you for this kind invitation. It looks like funeral, ceremony. Okay, so I would like to say that it's great honor to have opportunity to speak about the Institute in front of such a distinguished audience. I would like to start from acknowledging many institutions in Poland and many institutions around the globe, hundreds of them, for the 70 years of collaboration which have made possible what I'm going to present here. I will not refer afterwards, but please remember all I will show is a result of very extended and very fruitful and very pleasant, actually, collaboration which we have had over the 70 years. So, oops, must be somewhere. It's charging. Okay, sorry, it was charging. Okay, so Institute now, just to give you what size we represent, we have 400 employees, 20% from abroad, 46 professors, 7 women among them, and 3 academy members. And in addition, we have, of course, PhD students, and here 60% are colleagues from many countries. I think it's right to starting saying how we are indebted for serving for the community these 10 directors which were over the 70 years. It was very politically and financially turbulent times, and I would say, from my perspective, all of them are heroes that they decided to take Institute on their shoulders. Unfortunately, many of them passed away, and it's also a moment when we can go back with our memories to late director, late professors. I put several names. This list is far to be complete, and also it's symbol for all employees of the Institute who pass away already and come often to our memories. One person I would like to mention especially is Zbyszek Robaszewski, who was a student of University of Warsaw. Then he was working in our institute and did PhD here. And he was arrested several times during being here. And nevertheless, he got, it was, I think, error of security police, he got permission to go to Moscow in 1979. And actually, he went as physicist there, but it was meeting with Andrzej Sakharov between Helsinki Committee of Warsaw in Poland with Andrzej Sakharov organization in Moscow. So then he was sentenced for 4.5 years during martial law. He spent several years in prison, but in Free Poland he was 3 times elected to Senate, and for some time he was deputy speaker of the upper house. Present talk is about impact of Institute of Physics and impact of past activities. If you want to learn about present and about future, next talks will be devoted to that poster and booklet. I'm focusing on the impact of what was many years ago. So let's start from outreach activities. And here, it was already mentioned, we wanted to be, and we are, and we want to be in future, kind of champion in physics in Poland, but also highly visible in the world. And for instance, two institutes came from our institute, Unipress Institute of Molecular Physics in Poznań. In some sense, spin-off is Acta Physica Polonica journal, and also some companies. It's not ex-housing list. I would like to mention Unipan. Some of you may know, but not everybody probably. I like this equipment very much. I did many experiments using this lock-in amplifier, and you could find this lock-in amplifier from Kamchatka to Moscow over many, many decades. And second institute I would like to mention, which is spin-off, intellectual spin-off, it's Puremat. Andrzej Miecielski is running it up to now, and also Vigo, which comes from Andrzej Miecielski and Jacek Baranowski discovery of photovoltaic effects in this cadmium mercury telluride I will refer to. These detectors constructed by Vigo are not between Kamchatka and Berlin. They are on Mars. They are even more far away from here. And also we are very active over the years in professional organization. Professor Sosnowski was president of International Union of Pure and Applied Physics, and many colleagues were involved in European activities like ERC, European Innovation Council, and Academia of Europe. And out of 20 presidents of Polish Physical Society has 103 years, 4 were from our institute, and one of them was president of European Physical Society. There are many, many other, of course, institutes we can speak about, societies we can speak about. One I would like to mention is Polish Synchrotron Radiation Society, which activity was very instrumental to creation of Solaris, very successful National Synchrotron Radiation Center, which is in Krakow. Also, we organize hundreds of meetings, symposia, conferences. I mention here a few of them, in which number of participants were greater than 500. In particular, each year we are involved in the organization of EMRS, our European Material Society meeting. Each fall, it's in Warsaw. Also, we organize twice very famous International Conference on Physics of Semiconductors, also International Conference on Magnetism, and also of crystal growth, EPT2S, MSS. And last year it was very successful joint European Magnetic Symposium meeting in Warsaw, also organized by the Institute colleagues. Also, of course, on the local market, we had physics of magnetic materials, and we have had International School of Conference on the Physics of Semiconductors in Jaszowiec, which started in 1970, but is very active up to now. Here you see photo of last June symposium, and each year the symposium is organized by different chairperson coming from one of these institutes which are involved in organization and which are shown here. Popularization is, of course, we are very active in that, and physics Olympiads, international physics tournament, and for instance, one of our colleagues was president of international Olympiads in physics. Another colleagues organizes international physics tournament, which is very successful and started to be very international with 50 countries contributing to it. First step to Nobel Prizes, another competition, Physics P.A.S. and so on, so on. And also at the Institute, we are very actively collaborating with schools, and we have Science Festival contribution, Polish Children Fund for gifted children, and here Open Days and so on and so on. Okay. Core activities. There are 2 core activities. I would say first is education. It's an important part of our institute. Till now, we have had over 600 PhDs, successful PhD defenses, 200 doctor habilitation title degree, and over 100 professor title were delivered by our scientific council here. Also, we organized in the 90s when it was a very strong need for education. That time, maybe you do not know, in communist time, only 12% of children went to universities. Now it's 50%. And that time was need to create new education places. And several institutes, together with us, organized College of Science, which is now part of Kardynal Wyszyński University. And research. If one would like to say in 3 words what we are famous for, I would say we are famous for material development. And I give example of kind of influential publications, in influential journal at least, which has been published due to contribution of Institute in material science. We provided very good samples and made this research possible. Third word would be, in my opinion, theory, when again there is many contribution in the higher rank journals, And our institute contribution to these papers is to provide successful theory. Now publication. How many publications we have produced over the 70 years? It's around 12,000 with Hirsch factor 141. And here there is a distribution of co-authors of this publication, countries which contributed, which very nicely show how broad collaboration was and how many papers were produced with international collaboration. I also quoted kind of Guinness Book records. A number of publications has one record, a number of citations another record. Now, if we think about the impact, of course, you can apply thousands of criteria. One should not, of course, mix up quality with impact, but I speak about impact. And impact, if you measure, for instance, considering what activities were invited to be presented at important conferences. You can take another criteria, citation, to take papers which were cited more than H factor, so more than 140 times. It's another way. And this way is shown here, where number of citations of this paper is shown for various disciplines. So you can see what kind of discipline had some impact internationally, international visibility. And the lowest one, which has the highest impact, were honored by this Foundation for Polish Science Prize. And also it was this CRC Advanced Grant and this 10 million project, which was mentioned by by chair of this conference. Now, I will go very briefly by these different domains. Here is optics. Father of this field are here, Professor Białnicki and Professor Białnicka are here. And for instance, of course, it's very arbitrary what I put, but it's papers which were cited more than 140 times. And for instance, you see here stimulated Raman scattering and superfluorescent. And there is a figure which shows that if you increase intensity, line becomes narrower because quantum fluctuation contribution become smaller. This was a very respected paper showing very nicely theory of these two effects. Then spectroscopy and theory of diatomic molecules. But also very important was, and this is starting biology in our institute, was matrix isolation of nucleic acid constituents. And this was method which permitted to study this important biologically active molecules in environment a little bit similar to what in vivo actually could be observed. And now we are very famous also, and we have been very famous for fine rotational spectroscopy up to terahertz. There is a very effective broadband spectrometer and many nice paper about water, about organic, cosmic related particle has been produced in our institute. Now there is a small group who is very active and published tons of papers on computational photochemistry. And just to give you a feeling what it's about, I show the case of solvent-free electron. Maybe you know that free electrons exist in water, and people know that these free electrons are very active in many reactions. Yeah? You cannot describe a reaction involving water without this free electron. And it was shown that it is not the case. This free electron is not free, but actually this free electron is bound to this kind of clusters, of water clusters, and is quite extended. It's wave function shown here in green. It's extended, but still it is not free electron, but bound to this water cluster. So this had very important make a small revolution in our understanding of this chemical reaction I referred to. Then biological physics, as I said, we already investigated that many years ago, but then there was a lot of papers who said, let's use physical methods which we develop in physics to biological system. And I show one example. As you know, people are very much excited, have been excited about spin glasses, these ordered magnetic systems. And a lot of studies in various ways have been provided. And I show here one example that dynamics was studied. So you start from ordered spins, but if you have disorder, you have antiferromagnetic interaction, you end up with some chiral clusters, which can be left-handed, right-handed, and you can see distribution, if you wait long enough, how this probability of finding such cluster is at equilibrium and how this evolution occurs in time. And the same you can do actually with proteins. You have, you extend proteins and then you look how they fold, and again you can do the same game, find universality classes, dynamics, and so on. And also you see that you have similar graph showing left-handed proteins and right-handed proteins after spiral after some time. Then superconductivity. It was studied for years from beginning of Institute, but of course exploded when high TC superconductors were found. And here there are several important papers. One is neutron irradiation was employed to show that it pins vortices. As you know, it's very important for application to pin these vortices. Two gaps nature of magnesium borate was discovered, and also triple superconductivity, which is now very important for quantum information in ferromagnetic superconductor material. Magnetism, again, it is from the beginning was studied in the Institute. Again, extremely hard and soft ferromagnets were investigated. One group wanted to find hard magnet, another soft for different applications. And magnetostriction, theory of magnetostriction was very important here. And it was discovered, it's important that relatively cheap material, manganites, who have phase transition to ferromagnetic phase at a relatively high temperature, near room temperature, can be used for cooling, very strong magnetoelectric effects. And probably in the future this will replace various gases used presently in refrigeration. Defects in semiconductors. Now we move towards semiconductors. And if you go to textbook, you learn about this substitutional silicon, let's say. In silicon, you put aluminum or you put phosphorus, and there is electrons circulating around and so on. But studies done here showed that it's a rare case. Usually you have completely different structure of impurities. Even the simplest impurities like silicon and aluminum gallium arsenide is not one electron occupied, but there is negative Hubbard energy, and you have 2 electrons on the dopants. Also it could be anti-side defects and so on. There's huge family of discoveries. But one word is very important here is bistability. This defects under pressure, under light, under temperature can change its properties, which is very important if we think about optical memories. Another discovery was that we measure position of levels introduced by magnetic atoms. It could be a transition metal, it could be rare earths, and you order, it puts it in all materials the same energy, then you can find that there is reference energy, and from that you can determine band offset between various materials. Yeah? So it's very useful if you think about heterostructure. You have a tool by measuring level of this transition metal or rare earths to determine band offsets in semiconductors. And then narrow gap semiconductors. What was discovered many years ago here, but it's now very important, it's that mercury telluride has no standard band structure, has inverted band structure. We know that it's caused by relativistic effects nowadays. And if you mix up these two materials, this inverted band structure material, where again pressure was very important for the discovery, with normal semiconductor, at some point, if 10% you have cadmium, at some point you end up with Dirac cones, something which is known from relativistic theory. Oops. And you see a very interesting effect, that effective mass depends linearly on momentum. So it's kind of proof that you have this linear dispersion in this material. And as I already mentioned, this was important also to create material with narrow gap for infrared detectors and company, which was created afterwards. And then theory of these narrow gap semiconductors, it turns out that what you learn in books, textbooks about effective mass, the second derivative of energy, everybody teaches up to now, it's completely wrong. Actually, it's third derivative. It's first derivative. And effective mass defined in this way actually enters into everything you can imagine, density of states, mobility, thermoelectric power, and so on and so on. So it was kind of important discovery, and based on this discovery, theory of this narrow gap semiconductors with these non-standard bands, including these Dirac cones, were developed successfully. And also analogies to particle physics were put forward, which is now again very important. We speak about now Weil, Majorana fermions. Again, this is important for quantum information hardware. And this also brought discovery of topological crystalline isolators in some class of material. Again, due to this relativistic effect, we have funny states at the surface. Yeah? In bulk, there is a gap, but at the surface there are Dirac cones. And in some class of materials, the Dirac cones at the surface were discovered in our institute. And now, very famous works concern idea, which was what would happen if we combine magnetism, which was developing separately, with semiconductors. And it turns out one of the effects is that due to exchange coupling between band electrons, effective mass electrons, and these localized magnetic spins, if we polarize them by a magnetic field, is giant exchange splitting. And therefore, we could see how splitting of bands affects, or splitting of impurity level, or splitting of exciton, affects many, many phenomena. So we studied quantum Hall effect under this condition. We studied quantum noise, universal conductance fluctuation. And important that at that time we already had a low temperature, so we could see what happens at very low temperature. And actually, there is about 10 physical review letters which combines diluted magnetic semiconductors with a low temperature physics. Also, bound magnetic polaron theory was developed successfully. Maybe I could, sorry. Oops. And now dilute ferromagnetic semiconductors. What is the idea here? If we put carriers to the material, the carriers transmit magnetic interaction, and from this paramagnetic situation I discussed so far, we have ferromagnetic phase transition. And what was amazing, that in magnetic communities, it was believed that Curie temperature, magnetic anisotropies, magnetic stiffness, are parameters which are given by God. You measure them experimentally, but never calculate. Knowing these effects in semiconductors, well, we know very well how to calculate band structure. We know a lot about band structure. It was shown that we can insert this knowledge and calculate something which looked impossible to calculate. We could calculate theoretically and compare to experiment. And for instance, you see TC predicted theoretically with experimental values here on these graphs, and the agreement is quite reasonable. But also we showed, first there was theoretical proposals, and it was shown experimentally that not only magnetic field can affect magnetism, we can affect magnetism also by electric field. And another discovery, which was associated with beautiful material science, that if you, by doping, change Fermi energy, you change interaction, as I mentioned, you can change that by gating, and you change DC by gating, but also you change material science. If you change Fermi energy, the manganese ions from substitutial position can go to interstitial position. Also, correlation between magnetic ion spatial correlation changes. So it was kind of important physics here. And last point I would like to mention that even if you have no carriers, in some class of material, ferromagnetism is possible. And this is very relevant. You will hear today talk about quantum anomalous Hall effect. And this fact that ferromagnetism exists without free carriers is extremely important for nowadays meteorology. So I would like to finish my talk by thanking all generation for making our institute to be a vibrant and friendly institution. Many thanks for your attention.
Thank you, Professor Dietl. We may have time for one question, if possible, if somebody has a question, since we're transitioning to the scientific talks. There are some questions, but nobody's coming up with questions so much on this historical, I guess, presentation of our institute. So let me introduce, well, let us thank Professor Dietl again. Thank you very much. And our next speaker, so now we're transitioning to 3 talks which will talk about the current research of the Institute. And the first speaker will be Professor Tomasz Story, who's just getting ready here. Professor Story is the head of the Scientific Council at the Institute of Physics. He has done a lot of research in various topics in semiconductor physics, particularly transport and this hot topic of topological materials in recent years. And he'll tell us about experimental physics at the Institute of Physics.
Thank you very much. My task today is to use 30 minutes to describe experimental activities in this institute. I will cover the recent and just a few years back, no historical aspects. It's more or less mission impossible, and my idea how to do this is as follows. I will start with highlights. I will show you what we could accomplish, 3 examples in which I believe we are proud of and that demonstrate how we do top science. The very starting moment, I will tell you what is the experimental physics in this institute, because we do a lot, but not everything. No high energy, no nuclear physics in this institute. Later on, I will have to take a small walk through the institute to show you what is being done in which laboratory. That will be just cartoon, few points telling which field of branch of physics is being done. And please note, Institute is organized as 10 research units, 6 divisions, 4 laboratories. 9 out of 10 are engaged in experimental physics. In my perspective, the success of the Institute stands on the foundation, which is experiment and technology. This is the way I will describe it. You may share my opinion or not. At the end of the day, I will, oh, sorry, that was too fast. I will come to the conclusion that the way to do it is to make as good as you can technology, experiment on your own or with friends in the world that you can provide sometimes the expertise you don't have at home, and theory support, not somewhere at the end of the day, during the work. Along the time, the results are coming. And whenever we manage to meet the 3 of those items, we get results that we are proud of. So briefly, what it is. Don't be surprised that I start with growth. We grow single crystals. I will show you the examples, meaning the bulk materials. We grow epitaxial heterostructures. This is the 1 nanometer scale semiconducting, magnetic, superconducting materials. Once you have it, something grown, you need to nanostructure and nano-characterize. That needs special techniques. And we do have, for example, all these electron microscopy, electron and photolithography techniques. Then we formally come to the measurements, electron transport, magnetoconductivity, thermoelectric effects, superconducting heterostructures, is all there. Optics is probably the most heavy present in every department in this institute. Magnetism in all kinds of shapes and the experimental and theoretical research. We do have also a nuclear magnetic lab, EPR lab, thermal properties, you probably less know about it, but heat capacity and thermal conductivity are the properties that we study as well. Last but not least, biological systems, they have special ways to prepare specimens, special way to carry experiments, and this is the division, relatively new, but quite rapidly progressing. And now I can move to the highlights. The highlight number 2 I call the crystals. Large, bulk ones, and very small, nanometer scale. And it is my personal view that at the end of the day, technological facilities in this institute, that's the very basic, fundamental, experimental research tool. We are not producing for selling. We could, but we are not really doing that too much. We are producing for research. Whenever you need extra sample because it came from your research that you need extra one, we deliver. Not you have to, that's the way it's supposed to work. Okay, so let's go further on. So the description, bulk single crystals, just few examples. You can see the topological materials. They are here. The topological crystalline insulator, grown by a specially developed, patented, self-selecting vapor growth method. Andrzej Szczerbakov is the leader here. And these are the materials we did our topological studies. We do infrared studies. We do thermoelectricity. You can use the other technique, which is a abridgment technique, which allows you to grow very many different materials. The quality may be very high. Sometimes it's so high that you can seriously consider using them for applications. This is the bowl of cadmium manganese telluride produced by Professor Mycielski's group. It's 50 millimeters in diameter, and it has got all the properties required for the material to be efficient gamma ray and X-ray detector. Whether it will be really something in production or you just came with a material which is of equal quality as the ones already available, it's a tough time for moving into the real applications. But the crystal is there. It's a monocrystal, it's large, you cut it properly, you orient it properly, you make doping, you make it insulating, and then you come, here it is, the material that possesses detection properties equally good as the ones applied nowadays. And here the other option, optical crystals. We grow many of them. This is the laboratory of Professor Witkowski. You dope with rare earths. They get special color, but they get special spectral properties. There is plenty of that. I could take 10 pages like this, but I have only one. So it's there. It's maybe not the newest. It's the old-fashioned way of growing crystals, but monocrystals, if they are of highest quality, are indispensable. That's what I think, looking at the progress we have made recently. Okay. Now, we move to the completely other scale, 1 nanometer scale, and for that we need epitaxial structures. And this is the newest of IFPAN's technological facilities, a dual molecular beam epitaxy technological facility, operated jointly by Marktop Center and SL3 division. Here you can grow 1 nanometer precision, atomic resolution, quantum wells, quantum dots, nanowires, whatever you dream of. The Institute is the host of 9 ultra-high vacuum MBE chambers. That's the largest MBE center in Poland. We grow 2.6, 4.6, we do 3.5 with 2.6, combinations of that, semiconducting, magnetic, superconducting, optically active, thermoelectric. You ask, you get, provided that you stay within the material systems we have in our fusion cells. And we have 9 of such facilities, including the oldest one, grown, produced by our own during the embargo time, 80s. It's still working, providing materials. Now the question is, Professor Wojtowicz asked me to give a short proof how high quality can be achieved when you use these facilities. And the proof we together selected is, the first one is here. It shows you fractional quantum anomalous quantum Hall effect. Professor Klitzing will later on tell you about integer Hall effect, providing the standard of resistance for the entire physics, entire science. And this is something even more tricky, fractional quantum Hall effect, that is observed in just few material systems. So that is a stamp telling the quality is exceptionally high, not just high, exceptionally high. The electron gas needed for that, two-dimensional electron gas, has the mobility exceeding 100,000 centimeters square per volt per second. The same highest quality two-dimensional system supplemented with nanobars of magnetic materials was used to demonstrate in this science paper here. Sorry about that. What we call the action of spin transistor. I will not expand on it more. So it does prove you can do it. It doesn't mean that everything goes that nicely, but if you are persistent and you are equipped properly and you have good ideas, it may come through to the research at the level of, let's say, science publications. Okay, we can do more. These are nanowires, one-dimensional long objects that has very small cross sections. So there's a quantization of electron transport in X and Y direction. The freedom to move for electrons is only along the Z direction. We can grow all kinds of nanowires, gallium nitride, topological one, tin telluride, and the optically active 2,6 material here. You can see IFPAN here, this writing is done by nanowires. This is the selection of nanowires, and the trick here is that Professor Witkowski and his colleagues learned how to ask nanowires to grow here and not grow here, inhibited or allowed. And that's the result of technology, providing you with such a, maybe for advertisement, but the possibility. Okay, let me go further on. Example 1 completed. Example 2, nanoscale engineering of magnetic semiconductors. I am semiconductor physicist, so do not be surprised that I choose semiconducting examples. The reason I do will become clear in a minute. You say you grow materials, for example, nanowires, but you have to know what it is at the scale of nanometers. What it is in terms of composition, what it is in terms of crystal lattice, strained or not. It is important to see how sharp are interfaces. If you don't know it, you should measure it, forget it. You will be doing guessing. May work sometimes, but that's not really what we want. So these are the nanowires of different type. The one is gallium arsenide with all kind of shells. So we have the core and shells around. It's everything in nanometer scale. And now you can have gallium manganese arsenide an alloy for a magnetic semiconductor, the hero of spintronics research for many days. But you may equally have gallium arsenide matrix and manganese arsenide inclusions. And they are coherently embedded in the lattice. And they have very different properties. And this is our division SL1, Sławek, Kret, and others, to really give us the answer what we have grown. Is there a homogeneous system, or there are inclusions, or what is the case? And you can notice that we do have inclusions. The end result is that there is a matrix, which is not rock salt, not zinc blende, but Würzburg. And the matrix contains a coherently embedded nanoscale grain, which is of magnetic semiconductor, manganese arsenide. But that's at half of the history only. You have to move further. You see that there is a selection of possibilities here. Manganese arsenide can be in different crystal structures. And it can be either strained or relaxed. At the end, the result is, that's Maciek Wojciechowski's squid lab, telling us that the system finally reached manganese arsenide, strained in the Würzburg matrix, gives you the TC 100K above room temperature. Wow, one would say it's not quite what we wanted, that we wanted an alloy. But this is it. Is it good for something or not? Don't ask me, it's too early. But this is it. And now it's we are not just viewing what we have grown. We are modifying. And if you want, you can even claim that we are creating a new beast, because the people from electron labs, they can now hit during the measurement. So you can see how the grains develop on the picture. That's the level of expertise needed, the level of finesse and apparatus that you need to know what you are studying, without guessing or assuming that what you have drawn on in the book or given to the technology is the one that you got. So I end with the example number 2. I have to step further. Example number 3, one-dimensional topological systems at atomic steps at the surface of topological crystalline insulator. And this is the example of the situation in which our, let me say it, best in the world crystals need exceptionally high competence in terms of scanning tunneling spectroscopy experiments, which is the facility not available in this institute. So we asked for a collaboration. Paolo Sessi was the one to arrange everything with Würzburg University. It's called Experimentale Physik 2. These are the neighbors of Professor Molenkamp. And they have the facility. Matthias Bode is the leader there. And then you will see that this is, the beauty of this example is that it shows topology the way I am surprised anytime I think about it. Let me see what I tell you what I mean. If you have the monocrystal, the single crystal, that's the one here, grown by our people in division 1, that's not polished. It's as it comes from the technological furnace. This reflection is the real one. No games played at all. And then you cleave it. You go into the 10 to minus 11 Torr vacuum, low temperature, and you cleave it. It breaks. And it breaks in the form of atomically flat terraces. You can, this is the cartoon showing you what it happens. This is the crystal lattice, which is the simplest possible. It's rock salt, kitchen salt, that we all have in our homes. And it may break either with the steps that are 2 monolayer high or just 1 monolayer high, 3 angstrom or 6 angstrom. Now, nothing special, you would say, but that's not what it is. Then you do measurements. It's a busy picture. Don't worry, we don't need to understand everything. Please note that STM gives you topography. It tells you the elevation. And the stripes here that you see, they are atomically flat. You can see it here, the scan. Atomically flat, but separated by steps. The step may be 1 monolayer or 2 monolayer. And then you study the technique known as scanning tunneling spectroscopy, and you get the local density of states. So you check where there are the states, electronic states available for transport or for optical response or for magnetism. And you get quiet standard result, which is here. More or less, it should look like a triangle. When you check on the terrace or on the step, which is 2, 4, 6 monolayer, if you examine the step, which is 1, 3, 5, you get completely different response. And that's the sharp, strong, one-dimensionally shaped electron density of states. And the peak here is just the peak. And the question is how it may possibly come. You cleave a macroscopically large object. You get plenty of steps, and then you can do mapping. All the steps you can see. Either they are topologically non-trivial or trivial. 0, 1, Z2 topology at game. And it works that way. And it's an amazing experiment. I like it very much, not because I'm part of it, but because it's really a very special one. Okay, we followed, that started with 2016 science paper. Now we have PRL. Showing that you cannot, if these one-dimensional objects cannot be brought too close because they start to hybridize, and the new quantum systems that should be described not as 1 plus 1, but as a completely new double one. And that's the PRL, and the important message from this result is here. It tells you that the splitting starts below 30 nanometers, meaning if one day somebody will think about electronic circuits, the packing will be limited by this number. And that was determined in this research paper. We continued, and this is the result of this here. You can do all kinds of tricks. For example, you can surface dope these topological materials, which electrostatic fields will bend the electronic states close to the surface. When you do this, you may eventually qualitatively change the position of the Dirac point. You know, that's the middle of the Dirac cone with respect to the Fermi level. The game is to reach the situation in which electron transport will proceed through the states along the edge. And these states have the special form nowadays known as a flat band system. Flat band system means no K dispersion. That means effectively infinite effective mass, meaning no kinetic energy. And now if you come with electrostatic interactions that could be even very weak, if the competitor is almost 0, you end up in the situation when electrostatics is more important than kinetics. And that's the scenario for interaction and correlation effects to set in and to split the peak into two. It's important in that sense that the first determination that in those standard topological materials, we may eventually have to take into account electron-electron interactions and correlations, and they can change the topological phase diagrams of many materials if they are important. And we have engineered the situation in which they became important. That was my example 3. Please note, our crystals, but external expertise. Till today, Institute is not equipped with the facility that could do these experiments. Sorry, but that's the fact. Okay, let's move. Now, I finish with my 3 examples of research that I value or I like or I think it's important. Now, divisions, I have to walk rapidly, but division 1 is called Physics of Semiconductors. I'm part of it. So we do all kinds of things, growth of bulk crystals of different types, magnetotransport, magnetism of semi-magnetic semiconductors. We do electronic properties of topological materials, either synchrotron type research or magnetotransport. The cartoons that I present here, the first one is showing you the growth. And it's in the simple quartz ampule. That's the real experiment. Nobody did break yet the quartz ampule. It taken away this crystal which is here. It's a technology that needs 1/3 of this table. It's enough. It's very cheap. It works. Now the experiment is our specialty in a sense, this magnetotransport, Krzysztof Dybko's job. The point is that this a regular situation in which you have topological insulator that, however, is bulk conducting. Wow, that sounds like oxymoron a little bit, but that's how it works. There are defects. It's very hard to get rid of them. So we have the bulk 3D object on top, on the surface of which there is 2-dimensional special object of different electric properties. And how to get access to those special properties knowing that there is a shunting through the bulk. One of the reasons is to make to somehow exploit the difference that cubic has a different symmetry than planar object. Angle dependence may tell you who is who. And this is why we do it. This is why we have to analyze it. We do de Haas van Alphen, we do Shubnikov de Haas, all in this institute. And the analysis is here, and there is a theoretical model also that takes into account that the two systems can exchange carriers, which you have to be careful whether you have really the 2D system completely isolated from the bulk, or there is a way to exchange. And that's in the model of Professor Zawadzki. And then you get angular dependence, it's here, which goes more or less like 1/cosine. And the important point is the angles at which there are 2 peaks in the Fourier spectrum, one from one surface and the other from the other. At a given angle, I apply effectively normal field of different value to different facets. And this is the way we have interpreted these results. So this is the experimental access to topological surface states. People did it before us. It's not our invention. This is the application to this case, a very special one. Many times you have to be very careful that you properly conclude. Okay, next one, division 2, radiation physics and spectroscopy. Well, you can see what it is, molecular photophysics, experiments that support, and theory that supports all kinds of molecules that are important for photosynthesis, even more for life as such. Professor Sobolewski, probably we will hear about it in the next talk. Then quantum chaos, Professor Shirko is pursuing this piece of research. Molecular spectroscopy, for example, there is an important work, Professor Kisiel and others, science paper on water clusters, some time ago, but still have it. Laser spectroscopy of nanodroplets, and the new angle synthesis of laser ablation atomic layer deposition. The cartoon shows you the PRL with the cover, which is for publicity, very good. And the cartoon shows you the network, microwave network. You connect all the microwave waveguides in different ways, and you study the propagation of electromagnetic waves in this system. And there is a certain correspondence between the way the microwaves propagate, as described by the wave equation, and some very interesting and hardly solvable quantum Hamiltonians of the other systems. Apparently you can do both and see how it works, find sometimes solutions that are not visible but exist. I find it very interesting. It's maybe a little bit niche, I don't know, but it's, it's every 1-2 years producing very high quality paper. So this is how we see it. Okay, I have to move now. Division 3, it's physics of magnetism and superconductivity, I should add. They grow their own crystals, beautiful. The yellow one was grown in this lab. They grow crystals by Czochralski. If you want to see Czochralski facility, that big, maybe Professor Witkowski will be eager to show it to you. And these are the special ones because it require very high temperature. There is also this zone melting, it's called, this optical furnace. That's a very strong lab, doing also wire semi-metals as well as bismuth telluride systems. There is, of course, as it should for any magnetic group, SQUID and other magnetometry. There is the NMR lab, very well equipped, EPR spectroscopy. They study high TC superconductors, different superconducting materials, topological semi-metals. I have chosen 2 cartoons to illustrate. It's my personal choice. I can't be blamed for it. The one is here. It looks old-fashioned. This is the olivines. It's here lithium nickel PO4, important for some applications. The beauty is in the phase transition. Please note, this is the measurements of specific heat done in Professor Szewczyk's group. It is as the book tells you it should look like. But one is what is in the book, the other thing is to really measure. That's the antiferromagnetic transition. That changes upon applying magnetic field. A piece of experiment that I personally enjoy. And the other one, the same division is has the MBE facility with 2 chambers. That one is devoted to metallic systems, magnetic, superconducting. That's, I believe, Andrzej Wawro's group, showing you that you can make metallic, ferromagnetic, molybdenum, cobalt, here the example, wedge straight. Wedge means that there is multi-layer in which one of the layers changes the thickness continuously. It can be done with moving shutters. If you are a clever one, you can make a wedge in one direction and the other one in the perpendicular. That gives you the access to the range of points in which the thickness of 1 or 2 layers does change. Finally, you come with smoke magnetometry to see whether there is an interlayer coupling or possibly the Jaworzyński-Moryja type interaction due to molybdenum present, thus canting to ferromagnetism. And that's the atomic scale engineering of magnetic materials. Please remember some of such games, quotation mark, resulted in the Nobel Prize for GMR, and we all have GMR sensors still in our computers. Okay, let me move further. Division 4, a long name, Physics and Technology, Wide Gap Semiconductor Nanostructures. They have MBE facilities for nitrides, MBE facilities for oxides, different one, and LLD facility for oxides. They do optical spectroscopy. In particular, there is a device known as diamond anvils that permits optical studies at pressures of, say, hundreds of kilobars, maybe even more. They have also EPR lab, the second in this institute. And what I like personally, that the example, the cartoon, which is here, showing that sometimes you can combine optical measurements in the visible with EPR measurements. You would say, which is, as you know, the EPR, that's the energy of whatever, less than 1 milli electron volt, if I correctly count, maybe 1. And the reason is very simple. The optical response is determined by transition metal ions. Transition metal ions may adopt different charge states and different spin states. EPR is monitoring what is the charge state. Optics is telling you, is it yellow or rose or whatever they got, red. And that's the way you verify the idea of who is responsible for given optical properties. That's beautiful. I like it because this is, you blame this ion, but with optical techniques, you can hardly access its small details. And here the monitoring is for manganese 2+, because not every state, the charged state, gives signal in EPR, but monitoring manganese 2+ permits controlling the rest. This is a large division with plenty of results. Please, every of those pictures, you can probably find some of them in the booklet and in the posters. So please, I invite you to, if you are interested in something specific, to go there. Now Division 6, which is International Center for Interfacing Magnetism with Superconductivity, with topological matter, MACTOP, ON6 now in our understanding. There is a growth of MBE structures of topological insulators and vial semimetals. We do magnetotransport, thermoelectric measurements, also Solaris type photoelectron experiments. This is ARPES, angle, result, photo emission spectroscopy, and they collaborate on the STM, STS, as I already mentioned. The cartoons I have chosen show the thin epitaxial layer of lead-tin selenide, this one here. That shows the Dirac cone, and the experiment was done at Solaris in which they deposited iron or manganese, following the idea that in topological materials you might expect that the presence of magnetic ions will break the time reversal symmetry and opens the gap in the Dirac spectrum. It may do or not, that's a little bit more complicated. Here the gap is open, but it's not, I understand the explanation given here does not refer to time reversal breaking, but more to chemical type action of this. The other one shows you the complicated picture of the Fermi surface of the vial semi-metal, this very special object from the high energy physics that appears to be realized in condensed matter scenarios more frequently than in high energy systems. And please note, there are different pockets, that's no surprise, but if you read it carefully, you will see some pockets are labeled trivial, and the other pockets are labeled topological, and they come in pairs, plus, minus. There are two always, and together they have to bring the so-called topological charge 0. And now you have to get the data like that, which is a high quality, then the theoretician to tell you what it could be, then the experiment to verify whether it's really like that, and then you try to modify the surface by covering with extra atoms to see whether the system responds the way expected. Only then you can say, yes, this is the topological response, and this is the topologically trivial one, as they did in this publication here, and the PhD should be defended soon by Ashutosh Wage from MACTOP. Now we have 4 laboratories. They are meant as interdivisional type supporting labs. Nowadays this is independent research units providing us with the expertise that we need in electron microscopy, X-ray diffraction, X-ray spectroscopy. There is SIMS analysis, there is RBS scattering. We do have possibility to do implantation. That's the message to some of the research staff, which may not remember that we should use it more heavily, I guess. And then the experiment I've chosen that's beyond my imagination. This is the nanoscale diffraction. They call it, here is the name, let me see, nano electron beam diffraction. The end result is you have the nanowire with on the regular same picture. No, okay, there is a prolonged object with the proper dimensions. But now I say this object has a given composition, a given strain, a given lattice at the scale. Now I know what I really have grown. Is it good for my purpose or not? This calls for not only measurement in the electron microscope. We have this Titan 300 device, which is a few years old already, but still working. But it calls also for the methods to analyze they call it geometric phase, and finite element modeling. It's a complicated beast, but at the end of the day, it provides something that is extremely useful and extremely important. Now the division, the lab SL2, which is cryogenics and spintronic research, they have e-beam fabrication of nanostructures, the first in this campus, 20 years maybe, I don't know, maybe even more. They have ultra-fine squid magnetometry. Professor Sawicki is claiming that he is doing the best possible squid measurements of gallium manganese arsenide, for example. They studied diluted magnetic semiconductors, or we call them semi-magnetic semiconductors. Gallium manganese arsenide, there is also the nitrate system and the 4-6 ferromagnetic materials. They have also different group which is doing superconducting vortex electronics, quantum transport of spin and charge. And the cartoon I have chosen is from Dr. Zgirski's paper, showing you the experiment in which they claim to detect temperature of electron gas or electronic surrounding with the time scale of nanosecond. For that, they sent an electric pulse that is supposed to bring out of the equilibrium the Josephson junction, the superconducting second, and then monitor the response. Junction may be in the state in which there is a tunneling, like in Josephson effect, or in the normal state. Well, that's an advanced technique for me. It's on the poster. But apparently, this is something that is, if I correctly understand the situation, not achievable by any other means at the moment. Okay. And the laboratory SL3, this is the lab which is operating MBE facilities, 2 chambers, and also contributing to the other facility like MacTop. And they grow 1D, 2D quantum dots, quantum wells, quantum wires, and if you are very persistent, you may even get quantum dot, which is this prolonged object here, that has got core, shells, and along the axis you still have insertion of material of different composition, which is a quantum dot. It looks complicated, but it can be done. It shows optical properties as expected. You can force electrons and holes to either stay at the same part of the nanostructure or at neighboring regions, meaning direct or indirect type excitonic arrangements. The other piece is a little bit newer development in this group, concerns the use of the van der Waals crystals and these 2 transition metal dichalcogonides, the very fancy and broadly studied system now. And the game is here to use this Lego type stacking, but to find the important solution to important problem, that is how optically excite one material to transfer the energy to the other one without losing, let's say, the power or the coherence or whatever. This is being done. It's a competing technique. You can also do quantum dots with colloiding type techniques, Nobel Prize in chemistry. And so it's not easy to beat MBE, but it's different. Maybe I will finish with that. And the last not least, I asked Professor Niedźwiecka, the head of the biological physics, to help me with preparing this one. And the answer is what they do molecular biophysics. They believe they can contribute to the understanding of physical basis of biological phenomena at the molecular level. Sounds extremely important to me. So what it is at the end of the day, interactions, phase diagrams, conformation of proteins, biotechnology, biofunctionalization, and so on. One of the examples I give it here shows you the EDX, meaning the energy dispersive X-ray fluorescence, showing the quantum dots, very special ones. I believe it is given here. Looks complicated. It's natrium yttrium fluoride, a dot, that is doped with transition rare earth element for optical properties and protected environmentally with silicon oxide. And that one can go into the living body and use the property which is known as up conversion. In other words, you excite a given object with the light of a given energy, but it produces the light of much higher energy. You don't have to go with the high energy light through. It will come from the inside. That's the trick for this use in something that's called photodynamic therapy, or if I correctly read. That completes my walk through the labs. I missed many names, but I didn't miss any unit in which experiment is being done. I find it important, and the message at the bottom, advanced technology, good experiment, theory support online, not after time, remains the path to top science. The old approach I find still valid, and I believe our discussion on which way the Institute should go, which we have now, I like any directions, but that one I like very much. Thank you very much.
Thank you very much, Professor Story, for this rundown of everything that's basically happening here. Do we have some questions for Professor Story at this stage? A quick question, if somebody would like to ask before we go to our next speaker. Okay, so let us thank Professor Story again.
Thank you.
Our next speaker will be Professor Emilia Witkowska from the Theoretical Physics Division. She'll tell us about theoretical physics at the Institute. Professor Witkowska got her PhD at the Institute a little bit more than 10 years ago, I think, I'm not sure, 14 or something. And she carries out studies of ultra-cold atoms and quantum metrology. She has had quite a number of high-profile publications in recent years in PRL. Yes, please, Professor Witkowska.
Thank you.
The floor is yours.
As we could hear in our previous presentation, the main activity of our institute is experiment. However, I want to show you and convince you that theory also is going very well, and we obtain a lot of important results, and our activity is connected to the institute itself, but also we have a lot of common with another groups outside of institute. Theoreticians are working in all divisions which were mentioned by Professor Story, but in addition we have also division of theoretical physics. They all together produce dozens of papers each year with many important and interesting results. So I cannot say you everything, but I will try to show you overview of topics which could somehow reflect the activity of our theoreticians. So these topics are marked here by blue. They are representative, so we are working on quantum optics, topology, biophysics, soft matter, quantum dots, ultra-cold atoms. The research of theoreticians has different aspects. Some of them are support of experiment, describing them, propose experiments, and also explain results. There is a lot of work pushing our knowledge in fundamentals of physics. Also, a large part of the work connected to the European Union quantum flagship about quantum sensing, metrology, simulations, computation. And finally, also very important part of our work is to develop new theoretical tools and techniques that could be used to describe experiments or develop a new theory or found a new phenomena. So now I'm going to show you fast overview of many topics which are investigated theoretically in our institute with examples mostly from the theoretical physics department. So let me start with the first, which I call topology, which is very broad. This part of the work is connected very much with experiments in our institute. Great example is a paper about topological crystalline insulator states, where Professor Buczko take part in explanation and understanding of experiment. However, also we have another results, much more recent, which could understand very details of various aspects of topological crystalline insulators. For example, spin-hole effect or band structure and topological phases using ab initio calculations. A part of that very strong connection to the work of experimentalists of our institute, we have another works which are weakly connected to the experimental activity. For example, a very nice pattern formation by electric field quench in mode crystal, where Carmir took a part as a theoretical expert, and many, many others which I could not show you. Now, to be more concrete, I will show you a few examples of great theoretical results and projects which were finished very recently. First is about Rashba effect in quantum confined topological crystalline insulator. This work was done by Professor Buczko, Kaczman, Marta Hrabecka, and Rafał Rachciński. Together with experimentalists from Johannes Kepler University in Linz, they were able to study effect of structure inversion asymmetry on the electronic structure of this material. Theoretical work, theoretical results are shown on the top, and indeed, but they show that changing the thickness of this material, they could open the energy gap. And that was also in very nice agreement with experimental results. Second, very nice example of our work is the one made by Professor, by Professor Załuska-Kotur and Professor Katzman in collaboration with experimentalists from Weizmann Institute in Israel. They study a growth of nanowires via the vapor-liquid-solid method, and by using Monte Carlo calculations method, which is developed for several years by Professor Załuska-Kotur, they were able to understand the role of gold droplets in the initial states, so which are visualized here. They could show that this role is dual. They could serve as a collection center for growth species and also assist the nucleation of nanocraters in this material. So next example I want to show you, which is purely theoretical, by Professor Dietl. Professor Dietl studied the effects of charge dopants in quantum spin-hole materials. By using analytical and also numerical calculations, he could explain many properties of such a two-dimensional topological semiconducting material at the topological phase transition and in the regime of the quantum spin-hole effect. By presence of these dopants, he was able to explain many phenomena which appears in this regime of parameters. So I want to give one more example. This time by theoreticians from our group, from MACTOP, Misha Atif, Timo Yard, who studied the semiconductor nanowires with strong spin-orbit coupling in the presence of induced superconductivity. They could show that it can support topological Majorana zero modes. This subject is very intensively studied nowadays. They found some way to distinguish topological Majorana zero modes from the typical quasi-Majorana modes by observing different type of quantities and their behavior. For example, concordance, entropy change, and spin pumping. So that's a few concrete examples of beautiful results in the area of topology. Now I want to show you also a sketch of papers which are obtained in the area of spin qubits and open quantum systems. Spin qubits are quite strongly investigated nowadays, both theoretically and experimentally, mostly in the connection to quantum computing architecture based on semiconductor nanostructures in the context of quantum computer. We have, for example, beautiful paper by Łukasz Cywiński with his experimental friends, which study notch filtering, the nuclear environment of a spin qubit. Another very good example of quite recent paper is once more by Misa Atriv about Yoshiba-Rusinov qubit and possibility of their manipulation. In addition, in around this subject, there is also theory developed about description of open quantum system. And here I want to show you an example of a paper published in SciPost Physics Lecture Notes by Piotr Szańkowski, who first gave a lecture for our PhD students, and then these notes were published in the form of the paper. So that's also a very good example of our activity. To be more concrete, I want to show you example of one project by Łukasz Cywiński and Jan Krzywda, which was done together with experimentalists from Aachen University in Germany. They wanted to find a way to produce a scalable spin qubit shuttle device for coherent mid-range qubit transfer in silicon quantum dot nanostructures. They work a lot and they found a way how to move electrons on a short distance, and they demonstrate so-called claviature gates, which is illustrated here. It is to move electrons over many micron distance. Theoretically, our colleagues modeled how such a device will perform in the presence of realistic disorder and noise. So let's us move to another part of the subject, which is intensively studied theoretically in our department and also in our institute. I call them biophysics and soft matter. Biophysics is this interdisciplinary science which uses concepts and also mechanisms which known in physics to describe biological objects like membrane, like biological molecules in the examples I will show you. Here also there is a lot of various examples of beautiful results. I just give you a few of them on this slide. Main persons are here are Bartosz Rutyczycki, and he is also a very nice example of his work with co-workers, which was published in EMBO journal, but also plenty of another works by Professor Lee and Paweł Krupa. To be more concrete, once more, I want to give you a few examples of these results. Let me start first with result of Bartosz Rutyczycki, which was obtained in collaboration with Chinese Academy of Science in Beijing and also Nanjing University in China. They study adhesion of biological cells. And the question was how they respond to physical contacts between such as cells and between two membranes, which are shown here as a cartoon. Using statistical mechanics and Monte Carlo simulation, they shown that intercellular reception binding and also a shape of membrane and its fluctuations can lead to some reception aggregation within around such a contact. This was published very recently in Nanoletters. Another part of subjects which are investigated by theory part are led by Professor Lee and his students, and also collaborators from Vietnam and France. This part, I chose you this example, which is very important for everybody, about SARS-CoV-2 and how it binds to human cells. Professor Lee published several papers in this subject. I chosen the one which is from Journal of Physical Chemistry. They studied, by using molecular dynamics simulation, they could study how COVID virus binds to the cell of the human cell. They showed that the type of the SARS-CoV-2 binds to human cells much more strongly than the old one, SARS-CoV-1, which was known in 2002 already. Also, they play and they work with a many mutation of this virus, and found that in particular Omicron time binds to the human cell quite strongly, and they could predict that emergence of new variants with a higher infection rate could be possible in a near future. One more example, a work of Paweł Krupa from our division, is about creation of library which systematically show characteristic properties of fullerene basis nanoparticles. It is in the direction of drug design purposes. This work was published in Nanoscience with, in collaboration with theoreticians from Jackson State University and North Dakota State University. They, using extensive numerical simulations, they obtain site data and also put this data to large library, which could be used for future, either to develop a new type of drugs or for support of experimental studies to create a new one or to understand the properties. One more example. I told you I will show you a lot of them. This one by Panos Theodorikaris with his student and Piotr Dewar. They study droplet motion on different type of substrates. Here is an example on a brush gradient substrates. Panos prepared a beautiful movie to illustrate this movement. The idea was to show a way of a new design for such a motion and also design of brush gradient, for which it would be possible to move the droplet from softer to stiffer parts of such a substrate. So here's an example of that. By using numerical simulation, they indeed could show that the system minimizes its energy as the droplet moves from the rougher to smoother parts of such a substrate. It is toward the stiff region. So let me move once more to have more examples in the broad area of quantum optics and ultra-cold atoms. So that's the last part of our work which I want to present you. Here we have many beautiful results. I chosen a few which represent richness of the topics. So let me start with the results obtained by Professor Kozankiewicz and Irena Deprasińska about single organic molecules for photonic quantum technology, which was published very recently. We have also many work about exciton polariton condensation and single shot condensation of these exciton polaritons and the whole burning effect, which was published quite also recently in Nature Communication. Concerning fundamental science, there is very nice example by Professor Białyńska-Birula about helical beams of electrons in a magnetic field, and many other propositions for the experiments and study of fundamental science. Now I want to show you a few examples of concrete projects which were finished very recently. First is about topological optics. Professor Matuszewski with Andrzej Opala collaborated with experimentalists from Warsaw University to found a way to engineer spin-orbit synthetic Hamiltonians in liquid crystal optical cavities. These cavities is filled by liquid crystal. By applying of the external voltage, the spatial orientation of this long axis of the crystal could change and introduce index anisotropy. Then when two orthogonally polarized cavity modes of opposite parity was applied, it was possible to introduce analogous of the Rashba-Dresselhaus effect, which gives rise to the two cross-circular polarized eigenstates which are shifted in the momentum space, which is shown here. Indeed, experimental results agree very well with this theory and expectations. Second example of this group is about optical neural networks. Michał Matuszewski and Andrzej Opala, together with theoreticians from Singapore, propose implementation of reservoir computing in exciton-polariton condensates. This system is described by nonlinear complex Ginzburg-Landau equations, and this nonlinearity was very important in the implementation of reservoir computing. So that was a theoretical proposal, which later was checked against two experiments. The first experiment was made in Warsaw, in Warsaw University, by the group of Barbara Piętka. They could show that this kind of the computing neuromorphic binarized polariton networks can be implemented in exciton-polariton condensates in a lattice. Moreover, also they could show some simple binaural operations. Second example is implementation of this idea is made by experimentalists from Italy in Lis, and this time they could show that polaritonic neuromorphic computing even outperforms linear classifiers, and showing that this optical device is very promising and could be used in practice. Next example of topic which lies in the fundamental science is a proposition and the next realization of Pauli crystals. So here Mariusz Gajda, Tomasz Ksowiński, Jan Mostowski and Magdalena Załuska-Kotur in 2016 propose a way to not only observe but also to understand a ground state of a few non-interacting fermions in an optical lattice. So they could show by using Monte Carlo calculations that if measure single particle density, this structure which stands behind the few fermions blurs out, but if one measure higher order correlation function, it is possible to show that the ground state has a crystalline structure, which is shown here below. This idea was checked against experiment in 2021 by the group of Selim Joachim. He used exactly the idea and proposition of this group to measure such a coloration and show that indeed a ground state of several fermions has such a crystalline structure. Another very interesting example of activity of our theoreticians is a collaboration with CERN, which starts quite recently. So here a leading person is Tomasz Sowiński with his student, which took part in the consortium which name is AEGIS, which aim is to measure and check if antimatter feels gravity in the same way as normal matter. Actually, we know the results of these experiments, and Tomasz Sowiński will talk about that tomorrow. The role of IFPAN in this consortium is to understand a spectroscopy of antiproton atoms. So, including well-known, like positronium and protonium, but also there is a lot of questions about nature and fundamental behavior of medium-heavy antiproton atoms. Also, I think that we could hear about this subject much more today afternoon. As I told you in the beginning, also a role of theoreticians is developing a new tool, and here is an example of theoretical tool for description of driven dissipative lattice system. So this work was done by Piotr Dewar and also Michał Matuszewski, who works a lot about, Piotr in particular, is working a lot in the direction of developing new tools which could describe ultra-cold atoms, because exact tools are not enough, as they can describe only a few atoms, while in the experiments we have thousands of them. So that's why approximated numerical methods are necessary. In this example, they adapt the positive P and Wigner methods to such a driven dissipative lattice model, which can be realized in the excitant polariton systems. They show that this method is very efficient and scales linearly with the system size, is mostly independent of dimensionality. And here is a very nice example of results when the system is driven in the area of our logo. And they could show that indeed in this area the two-body correlations are well described by this method. And the last example, which is more connected to the generation of spin squeeze states, entanglement state, and also many-body correlation in the system of ultra-cold atoms in optical lattice, in the regime where they can be described by Ising model, Heisenberg models, Hubbard models. This is important in the scope of possible application, for example, in the optical lattice clock. And I refer you to the lecture of Professor Sinatra today. She will explain in details why they are important and what to do to generate such states in this system. Here I want to show you an example, our example, which was done in collaboration with the Professor Gediminas Jozelinas from Vilnius University, where we could show how to generate spin squeeze states in the system of ultra-cold fermions in an ultra-cold lattice in the mode regime, which this system can be described by the Hubbard model. By addition of additional laser coupling, which is nothing else like a Raman coupling, we could show that the system effectively could interact and generate necessary many-body correlations. So let me finish with this last example, and I will show just a quote of Richard Feynman. I have a hope that I convince you that the theoretical physics in our institute is very rich and interesting and useful, because indeed we were able to predict some new phenomena. We participate in description of experiments, in understanding of experimental results, but also we are trying to develop new tools and have some educational aspect in training new generations. Thank you very much.
Thank you very much, Professor Witkowska. We have time for some questions while Professor Witkowski, not related, is setting up. Are there any questions for Professor Witkowska? No? Okay, so thank you. Let us thank Professor Witkowska again. And let me introduce Professor Witkowski, Bartłomiej Witkowski, also from the Institute. He heads the ON24 division on oxide structures. And with Professor Marek Godlewski and collaborators, actually he has a multitude of patents, I think many every year at the Institute. And he's going to tell us about innovations at the Institute.
Thank you very much. This is a great honor to present presentation in such great anniversary. So I will talk about innovations for society. Of course, the Institute have many different innovations, but the keyword is society, so I will focus on the most important from society point of view. And the society looks in a different point of view than we researchers, and this can be very nice expressed by known citation by Paulo Coelho. Everything you have learned so far will lose its meaning if you can't find an application for that knowledge. So I am focused on applications. And I will start for application, we started with scientific innovation and turned into the real commercial applications. So a very good example for such activity is Pure Math Technologies. This is a spin-off company started by Professor Andrzej Micielski a few years ago. And this company produced manganese and magnesium for semiconductor technologies. And in terms of purity, this is absolutely world leader. It is a very known company with worldwide sale, Japan, Germany, US, Australia, Korea, Taiwan, and so on. Another very good example for such activity is software for deep level spectroscopy, which was created many years ago by Professor Leszek Dobaczewski and Krzysztof Gościński. And this is a very advanced tool for advanced laboratories. In group of clients, we can see CERN, NavLab, MIT, and is also very known and broad sale with, for example, Germany, China, France, US, UK, so really whole world. Institute have very broad equipment, technological and measurements. So of course we offer also services, for example, measurement services, many types of microscopy services, including TEM, SEM, AFM, and of course with associated techniques like EDS and cathodoluminescence. Also X-ray photoemission spectroscopy, diffractions, different kind of optical characterization, and many, many others. Of course, similar, we've got technological services. So annealing processes, lithography, deposition of different coatings, sputtering metals, and of course many, many others. Institute also is often involved in cooperation with industrial partners in projects, for example, funded by ANSI-BR. This is the list of the last few projects. They are related with thermoelectric modules, photovoltaic cells, gamma radiation detection, photonic instrument, and ALD reactor construction. Now I wish to start the main part of my presentation, which is focused on society and the problems of society, in which I think we physicists can help to solve. And one of the most important problems nowadays, especially in Poland, is problem of air pollution. Poland is the most polluted country in the European Union, and I think the air pollution problem includes inside energy problem and health issues. The source of this problem, at least at some part, is our energetic structure. So Poland get the energy main from the coal. And of course, during burning coal, we polluted our air with many different compounds, CO2, dust, methane, heavy metal, sulfur compounds, toxic substances, and radioactive elements. It has its price because the consequences are very, very bad. Different kind of disease, shorter life, financial penalties, and of course, cancers. But we need energy, and we're going to need even more energy. So what we can do? And I want to show our activities at the Institute, which are focused to help solve these problems. And the first perspective is how to obtain energy and our work in this field. When we think about energy acquisition, of course, the sun energy is considered as the most ecological and renewable energy. And the first choice is, of course, photovoltaic cells. The most photovoltaic cells present on the market are based on silicon. So we focused on this kind of photovoltaic cells, and we think about how to reduce cost productions and transform it to the more ecological technology. So we analyzed each step of production process of classical photovoltaic cells based on silicon. Of course, I will not tell you about each step, but some of them can be omitted, especially those ones which are using toxic substances and very energy consuming. So a few years ago, we proposed different kind of photovoltaic cell architecture based also on silicon, especially P-type silicon as a substrate, with flat contact with aluminum at the bottom, but with junction not with silicon, but with oxide nanostructures, especially zinc oxide nanorods, grown by the hydrothermal method developed here at the Institute, with combination with ALD layers. These technologies are very low temperature. On the top, we propose azofilm, which is zinc oxide doped with aluminum, which act as a TCO. This is very important because only contact on the top can be aluminum in exchange of the silver, which is very expensive. So this proposition, with this very simple architecture, we were able to receive 40% of efficiency, which is a very unoptimized structure. And this was the starting point for another R&D projects. We have a built demonstrator, which we show on the trade fairs to charge your mobile phone. And these works have resulted in many different, of course, publications, but also patents, including 2 European patents. And we were involved in a number of R&D projects and get the money from patent licensing. And some of the elements developed by us are still under development in other types of silicon photovoltaic cells, for example, PERC silicon cells. Okay, so now I want to go to the second perspective, what we can propose to save the energy. We analyzed what we spend energy for in household in Europe, and it turns out that the main part of the energy is spent on space heating. We like warm, but we also like to have very big windows because we don't have the big brightness in our homes. And weak link of our houses are windows. Heat is escaping by windows into two parts. The first one is the physical heat transfer, and people deal with it by multi-chamber windows. But the better we have windows, the better roof, the better walls, the infrared radiation becoming really important. So how to prevent heat escaping? We need coating for windows, which is, of course, transparent for visible light, because we want to have bright in our homes. Must block air, especially this close one, and high durability. And this is the main problem. On the market, there are some solutions which have very good optical parameters. Here's the diagram which shows light transmission in function of wavelength. This the green region is visible region. So here we want the transmission as high as possible, but going into far in infrared, we want this transmission go down. And these two gray lines, these two gray lines show the best commercial coatings for windows, but they are built based on metallic coatings, and they are slowly oxidizing. After 1 year, 2, and with every year, they are losing its parameters. So we proposed to use for this purpose zinc oxide with aluminum, which is known as a TCO in optoelectronics. And after optimization, we were able to receive almost the same parameters, but with much larger durability. We try to, for example, in different meetings and trade fairs, show people that is really important part. So we perform very nice experiment. So we use high-power halogen lamp to heat up the dark material. But between them, we put glass, and we measure how fast this material is heating up. And without normal window glass, after 10 seconds, it exceeds 40 Celsius degrees. But in case of such the same glass with coating, with the zinc oxide with aluminum layer, after 2 minutes, the temperature does not exceed 30 degrees. So this solution really works. The project related with this thermoisolating layers was ended in 2023, so this is a fresh project, and it already resulted in 4 patent applications, and we received some awards on trade fairs and industry events. Okay, now I want to go to the third perspective, what we can do to help solve the issue problems, the consequences of the air pollution. In Poland, approximately 50 to 60,000 deaths per year is caused by the environmental pollution. When we want to see the exact situation, for example, of different kinds of compounds, I show you the map of benzoapyren concentration in Poland, and we can see this is the really black spot on the map. And benzoapyren is the toxic substances, also cancer causing. So if we talk about cancers, the killer number 1 through the cancers is lung cancer, because it's not localized in the tumors as other types of cancers. So to fight with this cancer, we need new methods of diagnosis and therapy. And one of the propositions to help solve this problem are fluorescent markers. We recently talked about quantum dots, but we also proposed nanoparticles. And in this project was realized with cooperation between our institute and Warsaw University of Life Sciences in Warsaw. Especially in this Warsaw University of Life Sciences, we performed all experiments using animals. So we proposed zinc oxide and zirconium oxide nanoparticles doped with rare earth ions. We use this microwave-assisted hydrothermal reactor because this technology allows us to control sizes and shapes of these nanoparticles in large extent, and it characterized by very small size distribution. In the first stage of the experiments, we have to be sure that these nanoparticles are safe for living organisms. So we try on different animals. We tried if they are biocompatible. We have seen none of the toxic activity. And larger nanoparticles, I mean those about 50, 60 nanometers, are stable and detect as a foreign object. So they can reach almost all organs in the organism, and they can be thrown out by normal mechanism in living organism. Zinc oxide nanoparticles are slowly dissociating, so they're good for short time test. But zinc oxide, zirconium oxide, are much stable, and it can be present in the organism even for a few months. So this is good for long time perspective tests. Okay, but if we think about luminescent markers, we need sharp and efficient luminescence in these nanoparticles. That's why we doped these nanoparticles with rare earth ions, especially with terbium and europium. We built such a demonstrator to show on trade fairs that we really can control the color of this luminescence. And of course, it was very good publicated also in different journals. And now, how to introduce these nanoparticles into living organisms? People normally use intravenous introduction, which is very dangerous because it can cause nanoparticles aggregation and then can even block the veins. So this is why we proposed other solution, intragastric. So these little animals just drink solution with these nanoparticles, and through duodenum, it passes through the blood system and goes to almost organs in the organism, especially to the brain, because barrier between blood and brain is one of the tightest in the living organism. Okay, but can we do it for really to detect cancer? We did perform tests on animals on different kinds of organs, but I want to focus on lung cancer because it's the difficult one. So this blue graph shows luminescence of normal healthy tissue. We cannot for this experiment we used zirconium oxide nanoparticles doped with europium, so it should be red. So we have no sign of these nanoparticles in the healthy tissue. The healthy tissue have a very tight cell barrier, so these nanoparticles cannot go to these cells. But in case of cancer, we observe very broad red luminescence, and we are sure that nanoparticles enter at these cancer cells. The mechanism is connected with multiplying of cancer cells. They are multiplying very, very fast, so the barrier is not so tight. They have holes, and through these holes, nanoparticles go into these cells and stay in them, and we can detect them. It turns out that the same nanoparticles doped with magnetic dopants can act as an alternative contrast for resistance imaging. People normally used gadolinium compounds for this purpose, but sometimes there is need, often repeated this imaging, and then gadolinium compounds in such concentration can be toxic. That is why we need alternative markers, and these nanoparticles are very good for this purpose. And the last idea was to combine nanoparticles with medicine compounds, for example, with lectin, and use these nanoparticles as a transporter to different organs, especially for brain. And we performed such experiments. People from Warsaw University of Life Sciences performed. And we observed that nanoparticles with lectin go into the brain, and after some time, the lectin stays in the brain, and nanoparticles slowly are disposing from the brain. So this method can be used for this purpose. So these nanoparticles are fulfilling all requirements for fluorescent markers for living organisms. They are safe, they are detected as foreign object, they can reach almost all organs, they have sharp and efficient luminescence. We propose very good and safe method of introduction, and we see really the selectivity. We also show that we can use these nanoparticles for MRE and also for the targeted treatment of tumors. Now we almost finished the material science part and test on animals. To go to the human test, clinical test, there are need of lots of funds, and we are searching for partners who wish to go with us for the next step. Okay, at the end of my talk, I want to say a few words about program Incubator of Innovativeness for ZERO, which is a program of Ministry of Education and Science. This is important to be, as far as I know, we are the only one of the Institute of all Academy that has coordinated such projects. So goal of this project is raising the awareness of the scientists, building cooperation between industry and other institutions, assistance in finding partners and commercialization. But the most important part is financing of pre-implementation activities. Sometimes we have ideas that are focused on application, so they are not suitable for NCN, but its readiness level is too low for NCBR. And this program give us a very nice tool to finance such projects. And I very shortly want to show 8 projects which were financed from this program in the last edition of Incubator Innovativeness at the Institute. The first one is related with nanocoatings for implants, especially for patients with osteoporosis, where the integration between bond and implant is very, very important. So this is can have very huge impact on society. The second one is the technology of UV detectors, very cheap, very simple, but it should distinguish between UVA and UVB, because UVB is dangerous for our skin, so its potential applications are in life and health protections. The third one is also detectors, much more sophisticated, very, very fast, and for a dedicated spectral range, and have very broad potential application in lithography, science, medical, and also, of course, military. The next project was related with gallium nitride nanowires, brought by MBE, plasma-associated MBE, as efficient LEDs. So it has potential applications everywhere where the efficiency is priority. The next project was related with optimization of infrared radiation, operating at room temperature. So of course, this kind of equipment have very broad application, also in civil field as and military. Also, this software for deep level spectroscopy, which I taught at the beginning of my talk, it was also upgraded from funds of this program. It was attention to new versions of libraries and compilers, and also added 3D graphics. Also, the project related with thermo-insulating layer was also financed from this program. And the last one is very promising, is a method of modification paints and varnishes in order to obtain antibacterial properties using oxide nanoparticles, not silver. So just imagine we have a very easy way to get very large surfaces with antibacterial activity. And out of the end of my talk, which is really almost the end, I want to talk about promotion of the scientific results. Sometimes we got very nice results, and we cannot reach potential commercial partners from the companies to go with us on the program application. Standard method, scientific method, has publication, conference, presentation. Of course, that's very important, but it not can reach such people. Innovative fairs is also a good way. What is pretty much expensive, and the fairs are dedicated to different industry fields. So we, from the last years, we are starting organizing a press conference. And this is at the beginning, it was very difficult because the language we use must be much different than in scientific conferences. Presentations we show must be rebuilt from the beginning. But if we learn how to do it, this is a very efficient way to promote scientific results. And I want to show an example of our last conference, which was in November 2022. After a few weeks after the conference, we were present almost at all main television, national television, Polsat, TVN, and many different radio stations. There are over 500 articles in the internet related to our conference, and the AVE, which means advertising value equivalent, it was almost 1 million Polish currency. This talks how much we have to spend to buy such impact in the commercial way. But the most important thing is we found partners. We have already submitted grant applications, and another few are under preparation. Of course, these results were not only mine, so I wish to thank all co-authors of my presentation, and thank you very much for attention.
Thank you very much, Professor Witkowski. I think I'm standing in the bad place. Does anybody have questions for Professor Witkowski from the audience? Well, we should move to starting to ask questions because we're going to have visitors from overseas soon. I'd like to ask a quick question, actually, just to get things moving. So when you mentioned this infrared coatings, and so the ones that you have developed, they're more long-lasting. But how do you actually check that they're more long-lasting than the metal ones? How's that done?
It was built. It was based on the ISO films, which we work on this material for many years, over 10 years, and we measure optical parameters in other purpose. But after many years, we measure it one repeated, and they will not keep in some environmental atmosphere, and they have the same parameters, so nothing happens them, even to the presence of oxygen on water.
I see. So it's almost sort of like a fortuitous discovery in some sense. Okay. So any other questions from the audience? If not, then let us thank Professor Witkowski again. Our next speaker will be from overseas, and it'll be Professor Klaus von Klitzing from the Max-Planck-Institut for Solid-State Research in Stuttgart. And so for physicists, Professor von Klitzing needs basically no introduction because he's known, of course, for the discovery of the quantum Hall effect, and for which he got the Nobel Prize in 1985. We were hoping to host Professor von Klitzing here, but unfortunately, coronavirus intervened. So this is it is an example of the fact that we can't completely forget about this coronavirus. But thankfully, Professor von Klitzing is fine, and he'll be joining us by Zoom. If Professor von Klitzing is ready, we can pass the screen over to him.
I hope you can hear me.
Yes, very much.
Okay, indeed. And Röntgen stayed 11.5 years in Würzburg, and then he went to Munich and got the Nobel Prize then. And I just copied him. I stayed also 11.5 years in Würzburg, went then to Munich, but I moved already to Stuttgart to finally get this prize for the quantum Hall effect. And you see, I just added the name quantum to the classical Hall effect. And today I think quantum is the most modern word in physics. And as a member of the Max-Planck Society, I should rely on Max Planck as a Mr. Quantum. And in a certain way, we are preparing already for a big year 2025 because there's some announcement that we will have an international year of quantum science and technology with the subtitle 100 Years of Quantum is just the beginning. And I will speak today about this quantum revolution. Now, this new year, this 2025, started already 2 years ago when the International Union for Pure and Applied Physics, they triggered to have this year of quantum science technology. And at present, the United Nations will decide that we will start perhaps in January 25 at the UNESCO headquarters in Paris, this International Year of Quantum Science and Technology. And perhaps most of you remember the very successful birth year, the Einstein year in 2005. It was already mentioned this morning, this year 2005, where all over the world, also quantum science stayed in the front of the discussion. And I remember very well a special event in Warsaw in the year 2005. I was there and I attended the premiere of the Sinfonia de Moto and by Wojciech Kila. And the motto of this symphony was special tones, the G-E-C-H-I. And the Sinfonia de Moto was dedicated to the Polish scientists, written in 2005, the World Year of Physics. And in this motive, the composer enciphered the fundamental concepts and values of physics, the gravitational constant, the electron charge, speed of light, the Planck constant, the atom. And this, the fundamental constants, these constants of nature, these are now the basis of my talk. Fundamental constants, the basis of the quantum revolution in metrology. And I will talk about this in my presentation. Now, we have not only the music for the fundamental constant, a birthday cake for your celebration. And this was my birthday cake this year when I celebrate my 80th years, but it's a summary of my talk here. The focus will be here the new measurement system, our new international system of units. And the most famous example for this is the kilogram, a new kilogram since the 20th of May 2019. So this kilogram disappeared more or less. And the Planck constant, the most important fundamental constant in physics, in quantum physics, is the basis for our new kilogram. And this is a picture of our new international system. And my contribution is a small contribution, the quantized Hall effect. And I will speak about this special part of my scientific research. Now, Max Planck and the fundamental constants, all of you know that Max Planck is the founder of the quantum theory, and he was able to explain the black body radiation, and he introduced this Planck constant and this energy quantum, that the light consists of this energy particle, and he explained the experimentally determined spectrum of the black body radiation by the Metrology Institute, and his equation finally could explain the full spectrum, and he had to introduce the Planck constant and the Boltzmann constant to explain the spectra. And in his publication in 1900 was the start of the quantum theory. But if you look at this publication, you will see that Max Planck was more interested in fundamental constant and natural units than in quantum theory. He didn't believe that H nu has really some scientific meaning. And if you look at this paper, you will find here in the last sentences, with the help of fundamental constants, we have the possibility of establishing units of length, time, mass, and temperature, which necessarily retain their significance for all cultures, even unearthly and non-human ones. So even aliens should know something about this importance of fundamental constants. And Max Planck introduced these fundamental units for the length, for the mass, for the time, temperature. He added these Planck constants, the Boltzmann constant, the gravitational constant, and the velocity of light were already known. And by combining this, we have the famous Planck units. And unfortunately, they are not useful for practical application. 10 to minus 43 seconds, 10 to minus 5 grams, or 10 to 32 Kelvin are not useful in our daily life. And I'm very happy that Max Planck didn't include the elementary charge in his game, because then he could also write down this value H over E squared, which is an electrical resistance. And this is exactly the discovery of the quantum Hall effect. And the nice thing is that this resistance is in a range of 25 kilo ohm, which is exactly the range between insulator and excellent good conductor. So it's very well accessible in experiments. So we can use it in our daily life, and it fits really to measurements in reality. Now, the experimentally discovered quantum resistor, this h/e², initiated the introduction of a measurement system based on constant of nature. And indeed, the fixed values of these constants, Planck constant, velocity of light, Boltzmann constant, elementary charge, fixed values of these constants are the basis of the modified international system of units. And going back to the traditional international system of units, it's very important that all our measurements in biology, in chemistry, everywhere in the universe can be traced back to 7 base units. And these base units should be very well defined. These are the base units: second, meter, kilogram, Kelvin, ampere, candela, and mole. And we have now, since the 20th of May 2019, a new basis, a new international system of units. And I will just summarize already in the beginning of my talk the final result, so that all which want to learn something and which have to give lectures about our system will not make the error that perhaps he will tell that the kilogram is a kilogram prototype in Paris. This is not correct anymore. Today, really, the Planck constant is the basis for the kilogram. And also the temperature scale. We are familiar with the triple point cell, that the melting point of ice is a certain fixed point in our temperature scale. This is not anymore the definition of our temperature scale. The Boltzmann constant, fixed value for the Boltzmann constant, is the basis. And the same for the ampere. It's not anymore the force between 2 electrical wires. Today, the elementary charge, the fixed value of the elementary charge, the number of electrons per second, this is the current, which is the official definition of the ampere. And the same for the mole. We learned when I studied that the mole is a certain number of atoms for 12 grams of carbon. Also, this definition was replaced by a new fixed value for the Avogadro constant. So, and the quantum Hall effect triggered this development. And I will begin with the start of the revolution. The start of the revolution was 1980, and there was a new type of resistance. Now, I will not speak about Solidarność. It was also started in 1980, also some new type of resistance for more democracy. I will speak about the discovery of the quantum Hall effect. And since Mark Potemski from Grenoble is also in the audience and gives a talk, I have to show the famous picture of the discovery in 1980 at 2 o'clock in the morning in Grenoble. You see the red wine, cotillon, baguette, and cheese. This is Grenoble. And at this time, I wrote down the important equation which led finally to this breakthrough. And this is the important equation. The voltage is proportional to the current, and the proportional constant is a fundamental constant. So in Ohm's law, we have a new type of natural resistance. This resistance, which depends only on the Planck constant divided by elementary charge square of about 25 kilo ohms. This is a birth certificate of the quantum Hall effect, and the submitted manuscript to First of Letters was the title Realization of a Resistance Standard Based on Natural Constant. And I will focus today only on this aspect of the quantum Hall effect. It was really an unexpected result, because the research was really how to understand the motion of electrons in the most important device in microelectronics, and a silicon field effect transistor. And this is the original device where I made my discovery, the silicon field effect transistor. And I will not discuss here the physics in detail. The final result is just the current flowing through the device. One can measure a voltage, and the ratio of this voltage and the current is exactly this value, 25,812.8 ohm. The only condition is that we need the two-dimensional electron gas, which is realized in silicon field effect transistors, for example. And we need a strong magnetic field perpendicular to generate a quantum effect, closed orbits of the electrons like in atomic physics. So these are the two ingredients. If these ingredients are fulfilled, you can measure this quantum Hall effect. And I will just show a show curve. This is really an experimental curve. Here is as a function of magnetic field, the Hall voltage, the red line. In the classical picture, this red line is a straight line. And now one sees these nice steps. And here, the value of this steps is the Hall resistance, the Hall voltage divided by the current. And this is given just by the Planck constant divided by an integer and E squared. This is the plateau number 6, for example. Aspects, and up to now, more than 17,000 quantum Hall publications have the name quantum Hall in the title or in the abstract. And here is a recent publication about the impact of the original discovery of the quantum Hall effect. Here, I hope the connection works better now. In the color is the time, so before 2006 is blue, and the last 10 years is more yellow and green. And you see a very strong aspect of quantum Hall physics is connected to topological insulator. And we will have the next talk, Lawrence Molenkamp, and he's director of an own Institute of Topological Insulators now. And you see this topological insulator is one of the very fascinating aspects which are also covered here by the Institute of Physics in Warsaw. And the quantum Hall effect is regarded as the first topological insulator. Sometimes I show this picture of a ceramic with a gold border, and the ceramic is an insulator, but the boundary is a good conductor. You see here, zero resistance. This is a picture which looks like a topological insulator, two-dimensional insulator, but a real topological insulator. This is one material, and you have really, by the geometry, by the topology, at the boundary conductivity.
Tak, nie wiem, chyba szybko, będę się starał szybko wrócić. Będę chciał tam do siebie.
I hope that there's some noise now. Please, there's some noise. Okay. I will not speak about all the different aspects of this topological insulator. I will focus just on this small part of the quantum Hall effect, this application in metrology. Metrology with the Klitzing continuous effect, international system of units, Kimmel balance, spot balance, and these aspects, because this is related to my title of my talk, the quantum revolution in metrology. Because directly after the discovery, all the metrology institutes in the world controlled the electric resistance which were kept at the Metrology Institute. Here, for example, this was the official ohm in the United States. At the National Bureau of Standards, this was kept there, and by law, the official calibration for all electric resistance were based on such a wire resistor. This was a 1 ohm resistor in the United States. And they immediately started, after my discovery, to compare these wire resistors against the quantum Hall resistor. And you see here the measurements between 1983, 1988, and they found that if this ohm is by definition the correct ohm, then the quantum Hall resistor changes with time. But the real interpretation is that not the quantum Hall resistor changes with time, the wire resistor changes in time, because other countries showed the other slope. There are some strain in the wires of a wire resistor. There are some time changes. And here are measurements for 3 different quantum Hall devices, and they are all on the same line. So here it was demonstrated that the standards kept at the National Bureau of Standards are not stable, that the quantum Hall resistor is more stable than the wire resistor. And up to now, there are many, many tests about the universality of the quantized resistance. One has compared different devices from different materials, and I summarize here just some examples. The original discovery was on silicon. The gold Hall effect measurements is still gallium arsenide, and one has an agreement between these different materials with 10 digits. Later, different gallium arsenide samples were compared, even at a higher accuracy. Then graphene came up as an ideal two-dimensional system, epitaxial graphene, exfoliated graphene. Also, they agree with each other, and the so-called fractional Hall effect is also determined by h/e squared. And more recently, the quantum anomalous Hall effect is used also for high precision measurements of the quantized Hall resistance. And they found within the experimental error also agreement with the gallium arsenide. So in summary, we can say there is no significant difference at the level of 1 part in 10 to 10. This is just the experimental fact that we have in all two-dimensional systems where we see the quantum Hall effect, the same value of the quantization at this level of 1 part in 10 to 10. So this is an experimental fact. We have a very stable ohm, the quantum ohm, RK, h/e squared, and this is called the Klitzing constant, is more stable than wire resistors. And this is very similar to the Josephson effect, because we had already at this time of the discovery of the quantum Hall effect, the quantum volt, the Josephson effect, we have the superconductors and the Cooper pair tunneling. If you radiate this microwaves, you would generate this voltage, which depends also on the combination of the Planck constant and the elementary charge and the frequency of the microwave. And this worked also very well. The quantum volt was more stable than all electrochemical cells for the voltage. And therefore, we have here already 2 quantum phenomena which are better than other definitions of the electrical units. And therefore, already in 1988, the Bureau International pour Mesure recommended that a fixed value for the Josephson constant and a fixed value for the Klitzing constant, this value of 25,812.807 ohm, should be used by all metrology institutes so that we have the same values for all measurements in the world. So this was adopted in 1990, and in this way, you could see in the list of fundamental constants, conventional value of the Josephson constant, this value exact, no error. This was a fixed value, but it was a conventional value. The conventional value for the Klitzing constant was fixed in 1990 to 25,812.807 ohm, without any error. But the problem is, it was defined outside the official international system of units, because the official units, they in this way you should realize the ohm and the volt in a different way. So therefore, we had now this quantum volt with the index 1990, the quantum ohm with the index 1990, and these quantum units formed very stable these base units, and with the combination of these base units, the ohm should be originally defined as kilogram meter squared, about ampere squared, second to the power 3. But since 1990, everyone used these quantum units. But the problem is there was an increasing discrepancy with time between these units and these units, the quantum units and the SI units. So the conventional value, for example, for h/e squared in 1990 was fixed to 25,812.807000. Here we have 0.3, 0.4, 0.5. So somewhere here, this was a reference in our system since 1990. But the correct values, there are different measurements which can determine the value for this h/e squared. They were well above this original value. And in 2006, there was already 20, 30 standard deviations higher the h over e square value than the conventional value, which was fixed in 1990. So there was this discrepancy, and there was discussion since 2005 how to integrate the quantum Hall effect, the Josephson effect, into a new international system of units. And there was a big conference at the Royal Academy of Science, Royal Society in London, with the title, The Fundamental Constant of Physics, Precision Measurements is the base units of our international system. And the silicon MOSFET was on the cover of this publication. And there we discussed how we can generate a new international system of units. And very important at this time was a discussion about possible new definitions of the kilogram, because the kilogram was a problem in our international system of units. And this is shown just in this picture. Everyone knows that originally the kilogram was a prototype of a metal piece, but by comparing this official kilogram against the copies in the different national laboratories, one saw this time an increasing difference. So the kilogram in Paris was not a stable quantity. You see here the difference, and the Polish kilogram, for example, the kilogram copy number 51, this is the Polish one, was 1 kilogram of the official kilogram in Paris plus 227 micrograms in 1990. So there was an increasing discrepancy between different copies and the original kilogram in Paris. So it was not really clear which one is drifting, but in general, it was assumed that the official kilogram becomes lighter with time because the process of the production was slightly different and more gas is diffusing out of the metal with time. This may be the reason for the unstable situation. So we had this problem in 2005 that we had here in our international system of units an unstable kilogram. We had a very good atomic clock already since 1968, but we introduced already in 83 a fixed value for the velocity of light. And this was because by measuring the velocity of light, it was discovered that the meter was not well enough defined to measure it with very high accuracy. And therefore, the velocity of light and replace the original definition of the meter. And since 1983, the meter is defined by taking the fixed numerical value of the speed of light in vacuum to be this fixed number. So this was the first time that the fixed number for a fundamental constant was used to replace base units in our international system. And therefore, the idea was to integrate now also the Josephson effect and the quantum Hall effect, and to use fixed numbers for this value 2e over h for the Josephson voltage and h over e squared for the resistance. But if you want to introduce here two fundamental constants, you have to throw away two other base units, and one has to replace the ampere and the kilogram. And this is possible, and there are now experiments which are accurate enough to do this, to relate the ampere to a fixed value of the elementary charge and to relate the kilogram to a fixed value of the Planck constant. Now, it's maybe difficult to see directly how a kilogram is related to the Planck constant. I use normally this picture because everyone knows the relation E is mc square and the Planck's equation E h nu. And if you compare these two equations, then one sees immediately that there must be a connection between the mass on one side and the Planck constant on the other side. Velocity of light is a fixed number. Frequency is very well known from the atomic clock. So in this way, one can see this relation, but it's not realistic to measure directly this in an experiment there are other experimental realizations, and the most famous one is the Watt balance, which is called today the Kibble balance, and the X-ray crystal density method to realize the kilogram on the basis of the Planck constant. And the electronic kilogram is shown as a sketch in this picture. If one has the kilogram at the balance here, we have a mechanical force. Here on this side, we have electrical force. In principle, it's an electrical current in a magnetic field. And these electrical quantities can be calibrated with the quantum Hall effect and with the Josephson effect. And if we analyze these experiments, then we see that finally there's a one-to-one relation between the Planck constant on the left side and the mass on the other side. So this is one method to realize finally a kilogram by some electrical force. The other way is if we fix the Planck constant, then the Rydberg constant, which can be measured very accurately, then everything is well defined here. We have access to the electron mass. And the electron mass is given with very high accuracy, really in kilogram. The main problem was how to scale up from an electron mass to a kilogram. And one way is to go from the electron mass with cyclone resonance measurements to atomic mass or silicon atom, and then you scale up by measuring the lattice constant on a crystal, single crystal, and the volume to count the silicon atoms, and then scale up to 1 kilogram. And this is the second way, which is very successful. And so we can produce also a new kilogram based on a fixed value of the Planck constant by just producing such a single crystal. There's still a lot of problems because such a sphere is not really a sphere. To measure the volume is not easy. And at the surface of such a single crystal, you have from the polishing process some metals, some silicon oxide, some water, some carbon. But finally, one can control this to about 10 micrograms. So one is able to start with the Planck constant and end up with a kilogram with an accuracy which is high enough to use it in our daily life. Unfortunately, both the Kibble balance and this method gives the same value for the kilogram if we start from the Planck constant. So there was already 2005 the publication, redefinition of the kilogram, decision whose time has come. But it took another 13 years to have really this introduction of a new international system. And who decides about this international system? These are diplomats from 100 member states of the Meter Convention. And they have every 4 to 6 years general conference on weights, on measures. This was an old tradition of a conference. This conference, international conference, started already in 1889. This is one very famous conference. And at the last meeting last year, for example, they just decided that we should have new names for big numbers. 10 to 27 will be called Ronner, or 10 to 30 Quetta, and we will have no leap seconds for the next 100 years. So these are decisions how we can keep some international standards for measurements. But the most important conference was the conference in 2018, the 26th meeting of the International Conference, where one had a resolution on the revision of the international system for units. And I was invited to convince the audience that this is a good idea to have this revision. And interestingly, the coverage of this general conference in the media around the world was enormous. And the analysis has shown that the numbers of readers and viewers for the story as being greater than 2 billion worldwide. I cannot believe this number, because this would mean that 25% of the world population has heard something that we have introduced a new international system of units, especially a new kilogram. But he wrote that I don't think we can be sure that everyone of these read and understood the full story in full. Nevertheless, if even a small fraction followed it, then it was an event with enormous global impact for metrology and science as a whole. And the coverage was really enormous. I have here a picture from the New York Times, and there was this picture where the figure caption was, figure representatives of the meter convention voted anonymously to redefine 4 basic units of measurements, the kilogram, the mole, the Kelvin, and the ampere. Among them was Klaus von Klitzing, front row, taking a picture, discovery of the von Klitzing constant. And indeed, I see here myself taking a picture. I don't take pictures at conferences, but it was really very impressive to have standing ovations for a decision at a conference, for the decision for a new international system of units. And this was really a very special event, a historical event, because at this time, all countries agreed to have this change. Even Hungary, normally they like to have a veto, or Turkey, also the United States, the Russians, the Chinese, all countries agreed to have this change. This was the only international conference where all countries agreed to have some common decision. I think this will not happen in the near future again. This was really a historical event. And the final discussion result is shown here. And these are the recommended values of the fundamental constant. Here are the fixed values. We have now these fixed values for this constant, which form the basis for our international system of units. And in this constant, you will find also the Planck constant as a fixed number, the elementary charge as a fixed number, and then automatically also h over e squared and 2e over h, the Josephson constant, von Klitzing constant, are fixed numbers and are integrated in our international system of units. And if you look at the official site of the Bureau International in Paris, BIPM, the ohm can be realized as follows by using the quantum Hall effect in a matter consistent with some guidelines and the following value of the von Klitzing constant. And this is the value which has been calculated by the fixed numbers of h over e to 15 digits. And this value will never change in the future because they are based on fixed values. And this is a summary. Here, the value of our resistance standard. Up to 1990, each country used wire resistors, and each wire resistor had a different time-dependent changes because mainly the strain in the wires were different. Then in 1990, there was a decision to introduce a conventional value, so therefore we had at least worldwide the same basis for all calibration of electrical resistance. But this was outside our international system of units. And since 2019, everything is integrated in our international system units by the fixed values of fundamental constant. And therefore, the resistance will now stay constant forever. And the same can be plotted for the kilogram. The kilogram, we know that the kilogram was not stable, is small changes, but there are some changes, and there is a drift of the kilogram prototype. And since 2019, the kilogram is fixed by Planck constant. It should be stable. The uncertainty by measurements with balances was relatively small. And if we look today at the realization of the kilogram, the uncertainty in the realization of the kilogram is larger than by comparing two masses with a balance. So this uncertainty in the realization of the kilogram corresponds to the drift of our prototype kilogram in Paris during the last 100 years. But the accuracy in the measurements improves from this time and time. And at least we expect no drift of the new kilogram as long as the Planck constant stays constant. And this may be an open question. The open question how constants are fundamental constants. Are the time dependence of fundamental constant? And I can just say for metrology application, the constants are constant enough. We know today that they are with 18 digits per year constant, but it remains a fundamental question whether fundamental constant remain constant. What was the meaning of fundamental constant at the time of the Big Bang? And final conclusion is the quantized Hall resistance was better than expected. I was very skeptical when I saw the quantum Hall effect because measurements in semiconductor physics, they are always influenced by all kinds of dirty effects, by impurities, by surface, by contacts. And it was really surprising that the nature is in favor of the experimentalists and that we can use the quantized Hall effect with such a high precision. Thank you for your attention.
Thank you very much, Professor von Klitzing, for an amazing talk. I'd just like to say it's often, it's very hard to meet somebody for whom a fundamental constant is named. I don't think maybe it's possible with anybody else at the moment. So thank you very much. Are there other questions from the audience? We're not very questioning somehow today. Professor Levenstein.
What about the poor Candela?
Did you hear this? The question is, what about the poor Candela?
Okay, there are some very fundamental base units, but the metrology is for application. You can say the mole is more or less the fact that we have atoms which are building up the macroscopic masses. And I think the mole and the candela are not really so fundamental as all the other constants. But the metrology is important for practical application in industry, and to cover the optics and the chemistry to include it, we have to include also these quantities, but they are not so fundamental as the other units.
Further questions? I'm actually dying to ask one question, which is, if almost all these constants are defined as numbers, what remains to be measured to actually try to determine if some of these constants are drifting in time?
No, everyone focuses on the fine structure constant. The fine structure constant is a composition of different constants, and it's just a number. And in the spectra, you can see the fine structure splitting, which depends on the fine structure constant. And today, many groups are trying to compare different spectra where the contribution of the fine structure constant is different. And with the atomics, with the measurements, with the frequency comps, you can very accurately compare frequencies or transition energies this time. And now we are looking really, do we see a change with time of the contribution of the fine structure constant in the spectra in atomic physics? Or also in astrophysics, far distant quasars, where you can analyze the spectrum and you know from the redshift how old the light is. You can find out whether in former times the fine structure splitting in the atoms was slightly different. But up to now, there is no convincing publication which shows that the fine structure constant has changed with time. And today we have the accuracy of about 80 digits per year stability of the fine structure constant. So at this level, we have no change of these fundamental constants. But from the theoretical point of view, there may be, or there should be perhaps even, some changes due to the expansion of the universe or some other parameter. And I think this will be a Nobel Prize if somebody can convince the community that we have changes of these fundamental constants. But these are not important for practical application. In real life, we are happy with 8 digits or 10 digits accuracy in our measurements.
Thanks very much. Final questions? If not, let us thank Professor von Klitzing again. Thank you very much. And our next speaker, the last speaker in this session will be Professor Lorenz Molenkamp from the University of Würzburg, which was mentioned recently. He's famous for the experimental observation of the quantum spin Hall effect, which was basically opening up the field of topological insulators. This demonstration was in 2007. What's maybe less well known is that he's a collaborator of many groups with our institute, and he's also the head of the chairperson of the MAGTOP International Scientific Committee, which oversees the MAGTOP project and division since many years. So, Professor Molenkamp, thank you very much for coming, and over to you.
Thank you. My pleasure to be here. Almost this talk actually had the same fate as the previous talk, because my whole family, including myself, we were coronized until last week. But I feel healthy again. I hope that I'm not transmitting anything anywhere around here. Okay, so I made it here, and this is not the title I wanted to give. This is the title I wanted to give. I wanted to talk about something, well, this is a bit more perhaps related to recent research, but it also shows the relation that our group in Würzburg has to a lot of work that's been going on in IFPAN. This phrase, dilute magnetic topological insulators, everybody here will understand that this is actually something to do with dilute magnetic semiconductors, which is something that has been investigated here for 40, 50, 60 years. Dilute magnetic semiconductors are something that actually made me come to Würzburg, because this is the type of materials I wanted to work with to do spintronics with. And actually it turned out to be really, really nice to work with, to do spintronics on this material. And yeah, because of the interests of the Würzburg Institute, I directly got in touch with IFPAN already when I first came to Würzburg. And very soon thereafter, we had collaborations with Tomasz Dietl and Greg Garzewski, and then many, many more people from this place here. So this is talking now about work that we've done in Würzburg, but it's closely related to things that are ongoing here. So this is about the quantum spin Hall effect, which is kind of symbolized with this picture here on this front page. And it is basically what's happening to mercury telluride, which in my opinion was the first topological insulator. Klaus von Klitzing apparently disagrees. But mercury telluride for me was the first topological insulator. What happens to that if you add some manganese and get a giant G factor, as you know, happens in dilute magnetic semiconductors. And so this is just an overview of the kind of things that I will report on. Just some research work. We keep on continuing to work on it. So in 2D, if you stick manganese in mercury telluride, we see Kondo effects. And that's been a topic of investigation for a while, especially because, well, time reversal breaking is supposed to be unhealthy for topological phenomena. And actually, it's not so unhealthy as was expected. But you have to know the physics behind it, so that's what we've been going after. So these are 2D systems. This is zero field and then finite fields. And then in 3D, what we have recently think to have observed in these three-dimensional manganese telluride layers is the parity anomaly, which is something from particle physics that has been transplanted to condensed matter physics ever since the 80s. Well, you can debate on how successful all of these efforts have been. We think we have an interesting example of this parity anomaly. And then finally, if time permits, I'll talk about proximatized layers or proximatized with a superconductor, where in the end we think we have seen FFLO superconductivity in mercury manganese telluride, again aided by the giant G factor in the material. So this slide I can do pretty rapidly in this audience. So if you add manganese to mercury telluride, manganese is a 2, and because of that it's not a ferromagnet, you get a paramagnet. The spins on the manganese interact with the band structure, so you get a magnetization which follows a Brillouin function, and the giant G factor actually follows the same Brillouin factor and is enhanced. The material I talk about is typical density 10 to the 12, 10 to the 11 per square centimeter, so this is typical two-dimensional electron gas density. Mobility is not that great, 200,000 to 300,000, something like that. but good enough to see quantization effects. So the first thing that we asked, and we've been asking this for a very long time, is can we see quantized quantum spin Hall effect when we add manganese to our Merck telluride? And the other one is, if you go to finite fields, what happens to these S channels? Are they still there? Are they gone because time reversal symmetry is so broke to break anything? And what we found out in the course of these experiments is that there is a Van Hoven singularity in the band structure that actually strongly influences the things that we observe. These are 3 samples that I will talk about in mercury manganese telluride. And you may know that there's actually, if these quantum wells are topological, with an inverted band structure, if the wells are wide, so something like wider than 6 nanometers, and they're also, this distinction between topological and non-topological is depending on the manganese content, simply just like in cadmium, you change the band structure a little bit. And I'll talk about various devices. One device is in this direct regime. The direct regime is where you still have a peak in the valence band at gamma, which is higher than this structure at finite K, which is the camelback, which is basically what comes from the hybridization when you invert the gamma 8 bands, which is what happens if you make a topological insulator. So device 1 is a direct topological material, and devices 2 and 3, you don't have this peak anymore, and it's an indirect gap. So what happens if we add manganese to the quantum spin Hall effect? Well, theorists didn't really agree. There was a theory that said that, well, actually there will not be a very strong effect because, well, the manganese can flip 1 electron spin and that can backscatter, but then it cannot get rid of its spin anymore, so it's stuck and nothing really will happen to the quantum spin Hall effect. Altshuler had a very different prediction, basically indicating that you should get Anderson localization, so you shouldn't get any conductance anymore. And Matshaiko, this is Su Cheng-Xiang's group, actually said, well, we think you can screen away any Kondo interactions and any interactions with the manganese spin, which can flip the electron spins in the quantum spin Hall effect simply by a Kondo effect. So who was right? Well, it turned out to be that actually the first suggestion was the correct one. So this is an experiment on mercury manganese telluride. This is device 3, this is indirect material. And what you see here as a function of gate voltage is how the conductance at low temperatures depends on this gate voltage. So here you're in the conduction band, here you're in the gap region, and here you start entering the valence band. And what you see is that we see a very clear and also very broad and gate voltage plateau of a material where the Fermi level is the band gap, and we see the quantum spin Hall effect. So it's very very clear plateau. It's well quantized, as good as these things get. This is at millikelvin temperatures. We know there's always fluctuations. Well, they come from scattering to puddles in your material. And the plateau is very long, I already indicated, and this is, we soon realized, due to the camelback in the band structure. That is so, you get actually from temperature-dependent measurements, and that already gives you also more information on the other physics that's ongoing here. And what you see is that if you go from the lowest temperatures, which is what I just showed you, to higher temperatures, you see that the plateau gets shorter and shorter. And the other thing is that the quantization at 2e²/h somehow starts to get less and less clear. So you really have a lower conductance than 2e²/h, and that already points to a Kondo effect. So at these very low temperatures, there's a full screening of the Kondo effect, but at higher temperatures, you have still Kondo backscattering of the electrons, which gives you extra resistance. And so basically, if you look at the resistance in the gap, which you can define somehow as the more or less horizontal plateau, you see that the conductance is quantized as more or less 2e²/h at the lowest temperatures, and then it dips down. And if you go to higher temperatures, it comes up rapidly. Well, that is easy to understand because there you excite above the gap. But this is the behavior we want to understand, this behavior of the conductance quantization. And we also want to understand why the plateau is so much changing in width with temperature. Well, that's very simple. This has to do with the fact that we have this sample number 3, which is an indirect sample, which means that if we scan the Fermi level to the to the valence band, you get your Fermi level pinned to this camelback, which has a very high density of states in your material, because the mass is so heavy here, the electrons, at least at very low temperatures, are basically immobile. And now what happens, of course, if you now excite the temperature, you get a fraction of these electrons that are thermally excited to mobile electrons in the conduction band. And if you look at the Boltzmann factor for the excitation, you see that more or less that already gives you the same type of thermal behavior that you get experimentally in your conductance trace. So that is the width of the plateau. Now the quantization we compare with the theories of the Zeng group in the end. Which gives you using an interaction parameter of about 1/2, which is about what you calculate from the known dielectric constant of the material and the Fermi velocity. And so this theory of Matsuiko assumes what's called isotropic scattering. It basically means that your manganese atom, which do the backscattering of the edge channels, are always available for another backscattering event after the first one. It means that your manganese has to be able to lose its spin somewhere else. And we presume that this is other manganese or perhaps in the end hyperfine. There's always a way that you can lose a spin in such a relatively large probe. So what we get in the end for using this K value is a very good fit to the low temperature behavior using this theory of Matsuiko that gives you this power law behavior in the low temperature limit. It also gives another power law in the high temperature limit, but again, we cannot see that because we simply excite across the gap. So we can see quantization if we have manganese, and basically it's simply screened away by a Kondo effect. Now, take these samples and apply a magnetic field. So the manganese you can think of as locally breaking time reversal symmetry. What happens if this happens on a global scale? Well, this is the same sample. So this is a sample that was quantized at e²/h at millikelvin temperatures. This is RXX, which was quantized. RXY was 0, of course, or at these was high at these temperatures at this field. Now we apply a perpendicular magnetic field, just the normal quantum Hall effect configuration, and what you see is that very, very soon, well, you get some wiggles, but at very low fields already, you see a RXX of 0, and at the same time you see a quantization of RXY. So what it looks like is that you very soon come from the quantum spin Hall effect to a situation where I have a quantum Hall effect. And is this now real? Does this have to do with the edge channels? Are the edge channels gone, or is this a normal quantum Hall effect? So it's interesting to look a bit further into the physics of what's going on here. So for that we took somewhat bigger samples because then you don't have these size fluctuations that you have at very low fields. It's from the same wafer, but now you really see that the onset is already at lower temperatures. We see very good quantization of the quantum Hall effect at -1 plateau and zero conductance in the material. We can actually, with the position of the Fermi level, so this is scanning through the gap of your material with your gate voltage, we can actually push our plateau to occur. This is the first quantum Hall plateau. You directly jump to an n=1 quantum Hall plateau at something like 50 milliteslas, which may be interesting for all kinds of applications. So we can have a very low field quantum Hall effect. Now, what we've thought for a long time that we saw in these samples is something else that actually was predicted by Suchiang's group. It's the quantum anomalous Hall effect. Mercury manganese telluride is not a ferromagnet, but what you could do is, because of the difference in G factor between the H and the E bands in your material, what you could do is actually, if you have a large G factor, basically these guys both split up their spin in reverse direction. And what you need, of course, is the inversion between gamma 6 and gamma 8. And so the hope is that if you do away with the inversion of one spin direction, keeping one of the others, you could create a quantum anomalous Hall effect at very small fields. But it turns out that actually the fields that we see the onset of the quantum of the Hall quantization are at way lower fields than what you need and what you would need to actually do away with the band inversion of the upspin in this picture here. So we need another mechanism to explain the very early onset of this single quantum Hall plateau. And that turns out to be easily doable if you do a K.P calculation on this material system. So this is a calculation, K.P, in a type of tight binding on a strip. So you really have a lattice representing your structure. And you on each of the lattice points you do a K.P calculation, and that calculation gives you the edge channels that are shown in the dispersion here. So the color code is for the top of the sample or the left side, and this is the right-hand side of the sample. So at zero magnetic field, you have a dispersion of the surface states like this. And if you go to very small perpendicular magnetic fields, you will see that the Dirac point of the topological edge channels splits. That's understandable for spin up and spin down. So say the spin down goes up in energy, and there you have a very sparse manifold, so these states will still exist. But the spin up Zeeman level will go down in energy, and there it will meet again these camelback, where you have the high density of states. So you have a ton of states for the Zeeman point to hybridize with, and you basically lose that quantum state. So what you create out of these edge channels at finite fields still is edge channels. They're now hybridized with the bulk, but only one of them apparently has little enough hybridization to keep its quantization character. So you don't lose your edge channels when you apply a magnetic field. That was 2D. Now let's go to 3D. Topological materials. They actually have been predicted way earlier than, or predicted, they have been indicated way before the whole hype about topological insulators like 2007, 2008. For me, the first big example was this paper by Volkov and Pankratov from 1985. They were the first to suggest that if you have a reverse in band order across, say, the interface of a material junction, you will get a Dirac dispersion at this interface. And now we all realize that this is what was causing the topological surface states. At that time it was not really called topological, but in the narrow gap community, also with the people here of course, this concept was very well known. If you have band inversion, you will have this Dirac thing at the interface of your material with another material. So already in those days they predicted A, what we now call the topological surface state. And B, they said, in addition, if at this interface you can apply a large magnetic field, you will be able to pull states from the bulk towards your interface as well. And these are now also interface or surface states, but they're trivial, they're not of topological nature. And so these predictions existed for a long time, and somehow are not really discussed very frequently in the topological insulator community. Another thing at the same time, and more or less by the same people, but some more, is that you can have, once you have these Dirac systems in condensed matter, you can also think of doing Dirac physics in these materials. And one of the big things here, it was actually suggested by Semenov, is to look for the parity anomaly, which you have in all dimensions. Basically, if you have a Dirac system with a negative mass, there's an ambiguity in the sign of sigma xy if you let the magnetic field go to zero. And now it depends on the history of your system what you will observe. But that's a way to phrase the anomaly in a condensed matter system. And it's these people that are mentioned here that talked about it, especially Fredkin. I discovered the Haldane, of course, has this graphene-like structure with up and down magnetic fields. But Fredkin realized that, and already in 1986, he realized that you could actually mimic this parity anomaly in these Volkov-Pankratov inverted materials. He made the single mistake that he didn't let mercury telluride as the example, but let selenide, which of course is a crystalline topological insulator and not really a topological insulator. But already Fredkin really saw the physics and the physics implications of this band inversion interface state. So how do we want to see this? Well, it's better to go to magnetic fields and then finally let the field go away. What is the difference for Dirac electrons and their Landau levels in the magnetic field? Well, if the mass is positive, if you have a Dirac system with a mass and the mass is positive, there is a zero Landau level, a single one. And if the Fermi level is in the gap, basically you won't see it if you have a positive mass, a normal band structure. But if you have an inverted band structure, you have a negative mass, and you will have the zero Landau level coming from the valence band, crossing the gap, and then joining the conduction band manifold at higher fields. And showing this is for us basically the idea to demonstrate the parity anomaly. And so what you would like to see is, as a function of B field, this guy dispersing with B field makes your system going from inverted to non-inverted. And you should see at a given point, you should see the conductance of the zero Landau level go away. And that's what we tried to see in our mercury telluride, 3D mercury manganese telluride material. And again, they're using simply only the giant G factor to see it. And here you already can see the experiments that basically show it. This is just different. This is a material where we have top gate, and we can gate from the bottom because we use a gallium arsenide doped substrate here. And what you see here is basically the effect already. You see that at finite magnetic fields, we see the quantization in the material go from -2 to +1 to -1 and then back to -2 again. And that is this anomaly sign of this zero Landau level going through the Fermi level. So what are the states that we look at? Well, if you do this calculation, the K2P calculation on the system again, you will see that, now it's for the top and the bottom state, you will see that at the gate conditions that we are applying, we have p-type conductance in the top surface state, and p-type conductance in this material always has to come from a massive Volkoff-Pancrato state. So bulk states that we pull to the surface and that are then at the surface and give you a quantum Hall effect. So these are two massive Volkoff-Pancrato states. The reason we cannot get other p-type conductance at the surface is simply that the Dirac point is very deep in the valence band. So we have massive Volkoff-Pancrato states, two of them in the top surface, and at the outset of the experiment, we simply have one n-type topological surface state at the bottom surface. And that's what's giving rise to this, the sum of the quantization is then giving rise to the minus 2e squared over h at low field. And then at finite fields, what you see all of a sudden is that this topological surface state, which basically is this zero lambda level, goes away. And we go to minus 2 quantization. And at the end we go back to minus 1 simply because we have further quantization of this trivial Volkoff-Pancrato state. And so that's what we think is a clean demonstration of what we consider a parity anomaly in a condensed matter system. Now I am watching the time because I lost a lot of time to start with. What does Mr. Chairman want to do?
No, it's fine because it started a bit late. So
yeah, okay. So we take this material and mercury manganese telluride, and now we proximatize. We've been doing this a lot because you want to do things like topological superconductivity or whatever with these materials. This is also what's being pursued here. This is a quantum well, rather simple experiment, and actually the physics turned out to be also simple but a bit unexpected. We side contact with a type 2 superconductor, molybdenum rhenium. We see nice superconductivity, but we already noticed that to get the period of the Fraunhofer pattern to match with an area, we had needed a much larger area than that of the unscreened mesa. We really have to assume that a large part of the electrode is also giving rise to the period we observe in this experiment. That already shows you that somehow you get more magnetic field in the mesa than what you expect externally. So clearly the superconducting, the type 2 superconductor is actually pushing flux towards the mesa, and you see a higher field. This effect gives rise to very interesting hysteresis effects. This is a scan of the magnetoresistance of the material. So this is very high fields. We are not superconducting anymore, but this not in the junction, but the type 2 superconductor still is. And because of that, it can still do flux focusing, and it can do all its things with flux in the superconductor. And this influences the magnetoresistance. You would expect a normal parabolic magnetoresistance of these not so high mobility layers. And you see a very peculiar behavior coming out of what you expect to be the simple parabolic effect. And it's symmetric in field, in the scan direction of your field. And it shows a very peculiar behavior if you stop halfway your scan and wait and scan back up again. So, well, we were puzzled for a while, but it turned out that this is physics that directly comes from the flux behavior in a type 2 superconductor at higher magnetic fields. So this is so-called the Bean's critical state model, and that's playing a role in the magnetoresistance of these systems. So it's cute, no great new physics, but it's a cute effect. What's somewhat more interesting, I need to go back. So it gets more interesting if you now really look at the behavior of these Josephson junctions in a magnetic field. It's a similar quantum well. And what we claim or think to see here is basically that that the G factor in the material actually allows us, with an in-plane field, to scan the junction, the superconduction we have here, from a normal effect to a pi junction. And we get an oscillating order parameter in the material. This is the Fulde-Ferrel-Lelkin of Vishnikov oscillating order parameter in the material, which you only can get if you have a 2D layer with a large G factor. And of course that's what we have here. So what do we observe experimentally? Well, first we see this Fraunhofer pattern again with this large period, but I already discussed that. If we now apply an in-plane magnetic field, you see that this in-plane magnetic field really strongly influences your IV trace, and it does so in a non-monotonic fashion. It's plotted here. You see that the junction is the supercurrent is first fully extinguished by applying a B field, then comes back again, is then extinguished, and then comes back again. And so there's this really re-entrant behavior. And now you start thinking about FFLO. Now you have to be really careful because this is an in-plane magnetic field, and experimentally it's not so easy to totally have your magnetic field in plane. You could have some perpendicular to plane factor. But of course what we have is a giant G factor which is temperature dependent. So now we think we have aligned correctly, but now if we do the same experiment again, but now as a function of temperature, we should also see a oscillatory behavior in the superconductivity as a function of temperature, and that's exactly what we observe. So here we have a normal superconducting junction. Here we have a pi junction, and by referral we can also assume that actually with some small magnetic field we can at will tune our Josephson junction to become a pi junction in this material system, just using a dilute magnetic topological insulator. And yeah, just to show it fits, there is some theory by Sébastien Bageret, and he tried to fit it to our data. I'm not totally convinced by the fit, but it at least more or less gives the overall behavior that we observe in our material, and it's probably good enough to really make it stick that we are seeing this FFLO effect in our junctions. Okay, that's the end of my talk. So perhaps a bit more physics than previously, but I think most of the new speakers or later speakers will be talking about that. So adding manganese to a 2,6 topological insulator gives you an extra handle on doing the physics, and you see the effects both in 2 and 3D and also in superconducting materials. Thank you for your attention.
Thank you very much, Professor Molenkamp. Do we have some quick questions? No quick questions. How fragile is this FFLO effect to parameters, or is it possible to tell at this stage?
Well, it's pretty robust actually.
Oh, okay.
Yeah. So of course you can only do this if you have something that has a temperature dependence in this millikelvin temperature regime that we observe. But that for superconducting junctions, that's pretty normal. And so it's a robust effect, and you see it in each and every device. And
okay, so it's not just one device.
No. There's every device does it. Yeah.
Great. Thank you very much.
Okay. Thank you.
I see no other questions, so I guess we wrap up. Let's thank Professor Molenkamp again. And so that's the end of this session before lunch. So now we have a break for lunch. You can have lunch. There's a canteen outside. There's also posters in the hall outside. And we meet back here for those of you who will be back at 2:30 p.m.
historię zmienili.